So we will inform by evening all the schedule, everything will inform to you, all the arrangements we are doing. So by evening, tomorrow we are starting this, by evening we will come back around 8 o'clock like that, we will come back to campus again. So two organizations we are planning, one is the NRSC, National Remote Sensing Application Center Outreach Center, other is INCOIS, International Ocean Information Center. So there they will say about all the related to tsunami, everything, most of the related to ocean they will explain. So we will see how the whole thing will be there. So just we can start tomorrow, today's lecture schedule and lectures. So today plan is to one is like a, we will in the first my session I will explain about this, how the climate change impact we can see on the hydrological process, especially on the stream flow or in the available water resources in the particular basin, how it will impact in the present and future scenarios, how it will be there, those things we will see. And it is like a, most of you, some of you are asking yesterday, like it is like a, how most of these things whatever I am showing is the long term simulations. So present around we can say 30 to 40 years, future around we can say 100 years simulations. Most of the simulations are done in SWAT model. Okay, as most of you are asking, like we will plan anything is there one off day, like within the session we will try to explain you like how SWAT model will work also. That is also one of the very important hydrological simulation model. So you can we will plan so that we can experience or we can see that model also how it will work. And a lot of literature actually from our side, our group actually as Sridhar and our geoinformatics group working here, water source, we are working lot of related research work on the SWAT model. So you can see lot of papers are available, we can check those things. So now we will continue with the today's session. So climate change impact on the hydrological process. So we will see the how the climate change impact on the water resources and what are the important points whenever somebody is saying climate change study we are doing, means it should be like a little different than whatever we are discussing in the last few days. Like it is not like a only simple some flash floods, all the things. It is a different, like we need to make some long term scenarios we need to study. And there is a, whenever I say climate change, there is something called scenario, means most of the climate change we are looking at the future. So future means it's not like a 1 year or 1 day or 1 month, it's like a some 100 years or 50 years like that. So there is something called scenarios. I think last two days I think Sridhar is explaining like what are the scenario, how different scenarios will be there. So why we need to do the multiple scenarios to understand the climate change. So those things all we will see, and then some of those things once again case studies we are when we are carrying some research case studies on the basins, we will explain how those things can be considered. Then also like when we are analyzing those climate change things, we need to follow few things, that also we will see. And we will also like what is the general methodology in the climate change impact studies, we will check. Of course few case studies, and then I will present you the summary. So what is this climate change impact on the hydrological process? We will see what is the aspects we will see. We will see one is like a main thing is like a stream flow. So like whether the stream flow is it is like it is going to reduce, it is going to increase. What is the, you can say when the peak will come. So all the things. Oh, it is not on. So we will check all those aspects, and one other is like a important like a flood magnitude. So when the climate change is going to be occur, for example, what are going to be the flood magnitude? What is increasing or decreasing? So it's like all like a, with respect to time, with respect to magnitude, both things we will see normally. So then demand for water. Here demand for water means suppose climate change is there, means like a temperature is rising. Demand for water here means, for example, for the agriculture, like evapotranspiration, whether the evapotranspiration is going to increase or decrease, all those things also will matter. So of course other sectors will be there, but more like in the, especially the agriculture sector is there, and especially crop systems are there, how the, what is the demand during the climate change cases. That's one of the important thing people will see. And of course hydrological variability means all the process, for example, what going to be the groundwater scenario, what going to be the soil moisture, what going to be the like a water available for the crops, evapotranspir, all those things also we can see. Means variability. So climate is going to change means how it is impacting across the process. Those all things also we will see. And quality also, most of the times it is also important actually, water quality. So climate change is occurring, then how the water quality will change, what may be the possible cases, climate change is different, right, like long term, how it is going to impact on the water quality. So how we can see the water quality issues also because of climate change. Yeah, temperature will change a lot of, we can say activities which are there in the, you can say, water bodies or water. Okay, then also like because of this change in the way how the rainfall is occurring, very heavy intense rainfalls are coming, right, lot of a soil erosion takes place, lot of sedimentation will come, that will lead to lot of other activities in the water bodies, so that will affect the water quality. So it's one of the important you can say aspect also. So whenever you make the, you can say, this climate change, what are the points means like are you doing a simple like a global scale, at least like one you are studying like one state, one country, or one even the continent also, or local like small basin. We will see some of the case studies, like only we study one is small basin in the thing, and then small basin to big basin, those things we will show you 2 case studies. So that is depending upon the, you can say, thing that is very important, whether you are working on the spatial like a global or local scale. Then come to the temporal, short term or long term. Like a normally climate change impact studies on water source, if we will make a long term studies, like it is like called so future scale, like a next 25 years, next 50 years, 100 years, like that. Okay, they are called first feature period, second feature period, third feature period, like that. So then we will also see the only one process, only we are focusing on the water resources, or you are focusing on the, you can say, the groundwater, or you are focusing on the combined all the process. That is also we need to check before making the problem formulation. And of course, whether you are doing a systems type of thing, like whether you are standalone or integrated, means this climate change means like involves so many, you can say, multiple things, right? So many things we need to integrate. It's not like a standalone, like a one type of process will take care and we can understand the things. Okay. So here you see the data sets. I think last few days you are looking like a different problems, how the different data sets will be there. Only important thing here, you see all the things you are seeing, right? But this is the important data set for the climate change studies. So what is this one? Anybody can say why we require this one here? These are all things other day you are seeing, right? Every day they will come, but these are the extra. What are those things? I think Sir is explaining this rather like what are those different type of available, and then models, other things. So since we are understanding everything related to future, right, like next 50 years, those things. So we need to know that is like they are not occurred events already. We need to only just like a one scenario. We are thinking it may going to, or we are assuming that everything will go right now like this. What going to be in the next 50 years about the rainfall, temperature, other things. So for that we need to have this climate model data. This is important. One is global circulation models. Other is like a regional climate models. So global means everything, entire, you can say the globe means they will give the these models like what is the scenarios or what is the way the temperature, those things are going to occur. So with those things as a boundary conditions, so most of the there is a you can say centers are there each country. So they will do this regional climate model, means like they will run the regional climate models and then find the what are the like a high resolution climate data sets for the particular country or particular place. Okay, this will get from the, you can say, regional climate models. Okay, so it is like historic means like a whatever is the already like a last 100 years, like we have the whatever is there, right? So they will run for the historic data also, the same climate model. For that, why we require the historic data? Whatever already model is already done, right? Already climate is already we know historic, we means all the whatever the things we observe data is there, right? Still why we need to run the climate model for the historic data also? To validate the data set, means like for example I say some scenario, right? Once we run for historic only, we will come to know really that is setting or not. Since it is a model, right, we are giving some equations and we are seeing how it is going to come. So that's why always we need to run for historic, that is already we have to do, then we have to run for future scenarios. Okay. So when we are setting the hydrological model or whatever the models we are doing for our hydrologic process also, we need to do for both things. We need to run the model for observed data, we run the model for with same parameters, we need to run for the historic data, then you have to run for future data. So three things are required, then only we can able to make any impact study. Okay, we will see those things one by one when we are checking some case studies I will show. So these all things are already as I explained, just I will show you like this thing. Already this is like a world, like almost like at that time 2000 people are using these 4 scenarios. So and then just like a fifth, like a recently means most of the literature I think right now available in this RCP. Okay, so this RCP, what are the different RCPs you can say available? So 2.5, 8.5 RCP, like that's all the, you can say the available, like there are 4 scenarios, like a moderate scenario, normal scenario and worst scenario, like that 2.5, 8.5, like that we can say RCP 2.5, 8.5 like that. So like every 8.5 means what actually is like what is the amount of, we can say the energy, radiating energy is going to come in the future because of all those activities we are carrying out. Okay, so more I think already explained, we can see the slides or we can get those things, but we are more interested in this one. Now present, suppose some of you are really wanted to do something on climate change, means you need to look for these scenarios only. So they will only consider something energy like that in the budget, but now it is also socio-economic pathways. So this will give you the more mix, like a human activities and at the same time radiating energy, combinedly those things will be taken care. So accordingly these scenarios are derived. So normally whenever you make these things, you can you can use all these things, at least one normal, this like a SSP2 4.5 there, right? The worst scenario like SSP 5 8.5. So these things we need to run, at least your climate change models, these scenarios. Okay, so when you are doing the, you can say the projected data, so this is the thing, like we need, that's what I am telling, right? Historic and projected, both things we need to check. It's not just like you can't only go with the whichever you can say data. So we need to check for both the things. And here whenever I say climate change studies, there is a climate models, I will say, right? We have to run with the climate model data, but question comes like what climate model I have to use and how many climate models I have to use. Like hundreds, you see, at least like you see our scenarios itself. So whenever you can see like around 20 to 30 models will be there for one scenario. Like that, how many scenarios are there? 5 scenarios, means 5 future scenarios. So you can assume like that many number of data sets will be there. So there is no logic sometimes to run all the things. There is no logic also to check with all the models. What is the point in checking 20 models, everything to run and then check? So then what is the way out? So there is some process is there, step by step process is there. So something like which are the models best suits for a particular area. For example, our Indian subcontinent, there are only some group of models will work better. That to Indian subcontinent, for example, Krishna basin, Godavari, like different basins, different models will work. That there is a process there to find out available data set which is like a best suits for the particular area. So those models you have to take. That also like how many models to select. So in that you, for example, running for 20 models, right? 20 models. So there is a you can say there is a, you can see we compare with historic data and then observed data. Historic data is there, climate models, right? With historic data you are comparing with observed data. There are some matrices are there, like a you can say Nash Shakti efficiency, and then some other parameters are there, root mean square error, okay, R square coefficient determination. You check all the things, you take 3-4 parameters. So you see the models, each and every grid point. Okay, for example, basin, yesterday I am showing, right, some 7-8 grid points will be there. For those grid points, okay, each model you are running, right, for example 20 models. The 20 models, some 5 models may be like a giving best in all the coefficient matrices. So those 5 models you can select and then run the remaining scenarios. Okay, so in a basin normally each there is a 2 ways are there, each grid point you can select the best 5 models, or normally sometimes it is better also, for a basin you select a best 5 models. You see all the points which are the things, in that out of things you take a maximum models which are matching. For example 10 grid points are there, So around 7-8 models are matching. In that 7-8 models, how many best 5 models are matching? You can take and you can proceed. Okay. Then one more concept also there in the selecting the models. There is something called ensemble. You know, any of you know this ensemble models? So I am saying so many models, like what is the ensemble then? Hmm? All the models which are there like ensembled means like there is a 5 models I said, right? There is one option is run all the 5 models differently. But each model has its own way of simulating and getting data, right? So it's very difficult sometimes later like to see how that variations are there. Okay. Even then we saw that models also, there is a best way is like we can ensemble them. Means simple ensemble means like take the 5 models, it means 5 models average you take and get one average, right? That you run for the project future periods. Other way is, so in the model when you are running, right, each model has some weightage you will get. Like a 5 models are there means like you can see the weightages. Okay. So in that weightages, what are the weightages given to each model? For example, one model is best behaving based on the matrices, like we are giving weightage of 0.7, some model 0.3, some model 0.2, like that total weightage will become 1, right? So you will multiply each parameter like a temperature, rainfall with those weightages and then you will combine. Instead of simple average, you are giving weightages to each model depending on their you can say acceptability in that particular basin. Then it will be more close. So that data you will use. So you are getting right. You will use the ensemble data than the ensemble model data than the individual models. Okay. Selecting the best models, in that taking them as a ensemble. That's what is the procedure normally in the climate change studies. So you can see the normally whatever you do the simulation for the historic data, that is called baseline. Then next whatever you will do, that is called future periods. Okay. So you will do this comparison between the projected and observed simulations for the projected period. Means wherever you are doing comparison, right, what is the normally what is the climate change impact studies? So next 100 years if you take, in the first feature, how much stream flow is going to reduce or increase? That means which to compare? So we need to compare with observed, right? So observed we compare means you need to do that one, but there is chance of error. Yes or no? Why chance of getting errors? Since you are doing model, right, model has some uncertainty. There is some, you can say, model uncertainty is itself is one of the important factor. Okay. So you need to account all those things. Okay. So you can make this comparison and then you need to say that this much is the uncertainty which is going to be there in the model. So the calculation of uncertainty itself is one of the thing. Some of those things, Sridhar, I think one of the class is going to tell what are those uncertainty related aspects also. So then of course once we are making, then we can make these future scenarios, how we can simulations we can do, and of course this is what I am saying like an ensemble thing. So last part of the climate change studies normally anybody do, they have to do that one that is called adaptation. Okay, climate change is going to happen, water is going to increase or decrease. Then how to plan those things, like a crop will be there, crop like a how to cropping patterns, how to like a sectoral will be there, like a demand for industries, demand for some cities, or demand for different things, right? How to allocate the water based on the future water availability. So those things also we need to do, and normally people will stop at the only simulating for future what is going to happen, but the step has to conclude by suggesting adaptation. So climate change normally studies anything will be there is always better to end with the adaptation, starting with understanding how much amount is going to change, what is your plan that change is going to occur. Okay. So it's like a general flow chart, like most of the thing anybody want to do some climate change impact on the hydrological process or water resources, it is the general flow chart. So take a basin, take the model and take the climate model database, bring into the format of the complete database, geospatial database you can prepare, and so you can simulate using hydrological model different, you can say water balance components. Then you study the impact, how much is water, this particular parameter is changing, like how much evapotranspiration is changing, how much stream flow is changing, so how much is the temperature variation is there, all things we can able to analyze. Okay. So now you see the case studies, like what is the things. So here I will show the two broad case studies which we carried out as a part of the different research works, or the scholar research work or projects. Okay. One is like we are working we worked on the one, we can say the Munneru basin. It's very close as one of the sub basin of the Krishna river. So where So we studied like how the climate change really impacting on that particular basin, and we also studied like climate is changing means climate change will occur, right? So it is not only the climate change which is going to influence the hydrologic process, one more thing also will influence in the future. What is that one? So climate change is influence the hydrologic process, right? It will increase or decrease. Then what is the other spatial phenomena which will change this hydrological process? Land is land cover change. Normally both things work combinedly. So like only climate change impact and only land is land cover change, it will not be like that, right? So they are combinedly will impact in the future. So that way we made a study actually. So some of those results will present, and then you can see how really those things are there actually. So here we just the climate and alluvial change, how it is impacting. So here whenever you want to do this type of thing, you need the, you can say, this type of things. We need to have the hydrological models, of course, like as I mentioned, like a SWAT is the one of the best model for these things. So you can use other big model like that also, but especially climate change studies, SWAT is one of the best model. So and of course we need to have this climate model database for the present and future, and of course this case, since we are using LULC, we need to have the LULC also. So for this only I am saying like we need to depend a lot on the, one is like a BOVAN or NRSC, right, like data sets. So we can't go on preparing so many data sets, right? So normally that NRSC, their one of the main important work is every year they will prepare the land is land cover for entire India. So you can take for our area whatever is required, we can take, we can clip and we can use. So that's what is the thing. So otherwise you can go on generate means, so how many land use land covers will generate. For us, like when we are doing in the remote sensing, right, our own way, we can classify nowadays with the machine learning algorithms, and we can do. But there is always chance of getting like error sometimes. The classification technique we are following. So the lot of ground truthing we have to miss. Sometimes we may miss those exact ground truth things because of the different variation in the data sets. Okay. So means they have a lot of, we can say, field view data will be there, and they can do in a better way, especially land is land cover. So land is land cover Indian scenario is always best to check the data with the NRSC, best source. We can prepare, but it is always have to have the land is land cover from NRSC. Present the things. Free to download most of the things like a 1:50,000 data set, like a scale, that is also now available, and only one, there is a one document, means one signature letter will be there, especially the institute who are the students working, right, that guide or supervisor is there, they can say this is only for research purpose, means they can give. So they will send to the your, you can from our mail ID we are submitting, right, they will send to the mail ID and we can download. We did also actually for this Muneri basin, we did like that. So we asked the data, they provided complete data set. High resolution climate data sets. Yeah, that is I showed in the first class also. In the slide it is, even in the first day slides it is there. Indian Institute of Tropical Meteorology. So that is like a, there is a climate change wing is there actually. They are all doing this all things. I said, right, normally first of all data is available in global circulation models, GCM. But they will run for the CMIP 6. I think that somewhere I showed in the first class itself, CMIP 6, Climate Model Intercomparison Project 6. So there they are all like dividing the whole world into different, you can say, the zones, cortex, you can say zones. In that cortex zones, like our Indian subcontinent will fall in one of the zones. Okay. So for that Indian Institute of Tropical Meteorology, they will run all the scenarios and they will keep data sets. Yeah. Statistical downscaling you can do. Actually, now it is like a, for example, most of the data set that is available like a grid points, right? Okay, so it is available at each and every grid point, like the scale is like a 0.25 degree, 0.5 degree, or 1 degree by 1 degree. You want a like a further lower scale means, yes, you have to go for a statistical downscaling, or you may have to go for a dynamic downscaling. Dynamic downscaling means you have to use the RRF model, but normally that is more difficult. It is always better to go with the statistical model. Okay. So, but only thing is you have to always remember, we are doing statistical downscaling you are doing, right. Then later you have to do check for the bias correction also. So there is a correction will be there for the climate model data, right. It is a model data, right. We need to check with the observed data set. We need to apply the bias correction. So nowadays that Indian Institute of Tropical Meteorology, whatever the data they are providing, they are doing the bias correction itself, and then they are providing. They are correcting with already IM data is there, right. they are correcting with IMD data and they are providing. You can take, but always we have to check with the observed data sets. So we did all those that type of things. That's what I am telling. So once again, really you can check the literature which is available. I am gave at the end of this thing also gave the papers. You can check those things. So we made a systematic like a step by step process. Like somebody want to do that downscaling you are asking, right? The bias correction and combining the thing, making as a what we can call as ensemble model. How to make the best pi models. All things are available. So definitely you can check those things, and any doubts also we can clear actually. So our scholars also right now are available. We did all of those works are also available here, so you can get some clarifications also. So like a normally the because most of the times we use this QSWAT model, like a SWAT model. QSWAT means like a QJS. You are already working, right? So it is work with ArcJS also. Now it is even working on the on the web interface also. Some of that is all available on the website also, like on the as a cloud based also. But still that is like a they are different stages of thing. But this is like a very easy we can use. So we will possible we will make some time to show you also like a step by step process. So in this like a first this case actually the main aim is like a see the like how the climate data is going to, we can say how it will be there for present and future scenario, and how the land is land cover in the present and future, and how it is going to affect the hydrologic regime, means hydrologic process. So we will see some anomalies will be there, like really it is increasing, decreasing, where it is increasing, decreasing also. So this is all like a the complete flow chart actually. So here the one is like a we need to come with the land is land cover one side, and one side we have to come with the climate model data sets. So here the two scenarios I said like a best before using socio-economic, right? This is like a sometime back, right? We are using at that time this RCP 4.5 and 8.5. One is a normal scenario, 4.5 is a normal scenario, 8.5 is a extreme. One is called business as usual, means same way the for example people are doing, they are not going for any extreme things like a lot of industrial development like that, then things will go like that. Lot of industrial development, they are not following any guidelines of the environmental protection, then it will go for RCP 8.5 like that. That's why always both in RSC you have to run whenever you are running a climate models or working with climate models. So this observed data, so this all will come as a input to the SWAT model setup. So there we will first do the calibration, sensitivity analysis, then we will do the analysis, the outputs. We will see step by step how we can do those things. This is the basin I am saying about. Munneri basin is the sub basin of the Krishna river. So it is like a almost starting from the Warangal, wherever right now we are there, it will start from somewhere here and it will all the way flow to the Krishna river and then finally joins with the Krishna river. So this is like a, we are made into different sub basins, and these are the climate grid points, okay, and these are the major soil means land is land cover. It is basically these areas are the something called maybe the where there is a lot of most of the area is agriculture, cropping is agricultural based watershed only. Very few cities are there and very limited you can see the forest areas are things. Most is like a agricultural dominated basin it is, and it is not a very like a simple undulating terrain. It's not so like having a lot of hills. It's not like that. It's like a undulating terrain. So this is the you see that's what I am telling. It is like a varying from, of course this is the range like a very that's like a place where we are right now there, this area, to the place almost getting the plains. This that if you go. So here these are the maximum is also soils also not so variant. It is almost like a this is type of thing like a block cotton soil, this area, right? So most of the things this also like a block cotton type of soils only this basin, and maximum crops growing in this basin are the paddy like a rice, and then other one is like a cotton, because that is the major you can say types of crops, and then so you can see some of these things. So here we made the into sub-basins. Since any study we want to make in this thing, right, we need to make SWAT model always. What is the fundamental like a building block in the SWAT? SWAT anybody worked, right? I think some of it said that you are worked already. What is the building block in the SWAT model to build all these things and then run the process? HRU. So what is the full form of HRU? Hydrologic response units. So whatever you give data, you give dam, LULC, and then you are giving this what you can the soils. So with combining all the things, it will make into hydrologic response units. those response units will where you are providing the input, it will take all those inputs whatever you give, like a rainfall, temperature, those things, and it will generate the, I can say, by SES curve number technique or other techniques available in that one, it will generate the excess rainfall that is giving to that you can say this basin. So basin then will route the water. Route means erode. That's like, for example, this water is falling here, then what is going to be the outlet, it will simulate by using routing algorithms. Okay, so here like each basin contain the HRUs, and a combination of HRUs will make the they are called sub basins. Okay, so what is the main advantage in this SWAT model is you can simulate at the end of the basin. For example, you are doing simulation here, but what is the interesting thing or important thing here is you can do analysis later you want, you can do at a smallest level. For example, something is happening here in the some hydrologic response unit, like at particular land is land cover, also you can do, you can study. Okay, so for example, that's some of you, I think as like you are studying maybe, or you can you are planning also, like there is something called adaptation I told, right, and there is something called you can make the some change, you can bring in the watershed. Okay, so those things actually the like they are called best management practices, they are called BMP. You heard about this BMP, some of you? So best management practice, you can see some HR, you plan something, right, how the response is going to come at the basin outlet, you can study. So you can change something, like you are constructing something, or you are changing some crop there, or changing some cover there, then accordingly you see how the response is going to come at the outlet. That type of things we can study. That's the main advantage of this SWAT model. So whenever you are using this SWAT model, right, here are some of the things like these are all the something parameters. So SWAT model you are working already, you may know, like there are like you see these are few parameters which shown here, but there are so many parameters will be there. And here you see this like dot GW, okay, dot SOL, dot HRU. What is the meaning of these things? So for example, this is a parameter at HRU level, this is important. Means you want to replace this value, means this is like a calibration stage. Calibration means what? So you are simulating, right, model, you will get some runoff, but we are comparing with observed, right? So during that time you need to you can say calibrate the all the watershed parameters. One is curve number, and this is like a groundwater parameter, and it is like a groundwater delay recharge parameter, and soil AWC means antecedent water content. So these are all the things are very important. Okay, so some is depending upon the land cover, something on the groundwater, something on the management, like this all the parameters will be depending. So you see each parameter there is some minimum and maximum value will be there, right? So that is like a tuning. So we need to tune the, I can say, our model by keeping the value in between. So that is also when you are doing, you have to be very careful. You can't give some unreliable value in the thing. For example, hydraulic conductivity for a black cotton soil. Normally it is like a very small. Since you want to calibrate your model, you can't give something like a very high value. It will unnecessarily, it is called high calibration. So it later it may not give you a perfect resemblance of the hydrological process. You have to make a, that is called lot of, you can say, work. This is itself is a very important work in the SWAT model thing, that is called model setup. So it is like it will take some time for you. So you take the observed data set, observed rainfall, temperature, all the parameters related to, we can say, those weather, and same thing like observed runoff. So with those things you are going setting the parameters, all those parameters we need to calibrate. Once this is done, your model is set up, right, then you can do for the historic future things, you can simulate. Okay, so you can see full form of these parameters. Okay, and range, you see whatever the range you are giving, definitely they have to be in the range, and that too they should be reliable values. Okay, so it's like a trial and error process. Okay, so trial and error we can do initially, but how many trial and error we can do? It is very difficult, right? We can go on number of trials and those things. For that there is a one setup is there in the SWAT model. Any of you tried the setup? What the setup? Anybody tried in the SWAT model, that type of setup? Somebody worked with SWAT model? You are saying. So there is something called SWAT cup. What about that one? SWAT cup. So especially is only meant for improving this calibration process. Okay, you can do manually this calibration, and you can use SWAT cup also to make it automatic, like it's something like called optimization model. So you give the starting and end range, you will give, you can give the observed data, you can give the simulated data. Then it will go on make a number of runs, and it will give a best fitted parameters, for given that we can say by reducing the difference between observed and simulated values. Okay, so that is normally the you can say we can do in the SWAT cup. So normal practices people will do manually first sometime. With those parameters they will give input to SWAT cup and they will try to get the final things. Okay, so this is the way once after doing this during calibration time you can see this one. So it will tell so many things. It is like a in the SWAT model itself there is one of the output you can say place. So you can see the a time and it is like a value of the you can see the discharge. So you can see this like somewhere thick lines will be there, somewhere the thin will be there. What are these things? There is thick band is there, sometimes very thin band is there, and there is you see there is the observed background whatever is there, and there is a simulation is there, and in between there is a all showing this thick and thin these things. What are those things? That is the you can say difference in what is our observed and simulated things. So the band thickness is increasing means what? There is more uncertainty. Whatever you are simulating, uncertainty is there. So we need to go on reducing that one. We need to make a number of simulations, number of changing values, and you need to make a number of trials. Okay, and in this there are two important parameters. These are all important. There is one thing called you can say Nash-Sutcliffe efficiency (NSE), and there is a R square coefficient determination. So those two parameters you need to check what is the value it is going to come. So I will show you sometime those things also here. Actually we kept some of those parameters, and it is also there actually here. I could not see from here, but it is that value also there here somewhere Nash-Sutcliffe efficiency and R square. So those values we need to check more. Of course every parameter we need to check whether they are really correct or not, but those parameters we need to check those things. I will show you there is a. So finally after you do that one right number of in the simulations, so then you can compare what is the observed data you are doing and what is the simulation you are doing. So this is a stage, it is a model setup stage. So we need to make something for calibration and something for validation. So calibration means what? You are changing parameters and you are simulating. So till it is you are getting a best thing. Validation means just simply you will use same parameters you will not change. You will run for the data set and you will check whether how the we can say various you can say errors are there. That is called validation. Normally rule actually the data is available right, like we need to have some observed data for set for to doing this one. Okay, it is like a 70-30, 80-20 like that. You are getting right this formula 70-30, 80-20 like that. 60-40 means 60% of data for the calibration, 40% validation, or 70% for calibration, 20% I mean 30% for validation like that normally. So some people will ask like a question like for example 50 years data is there, first 20 years we can do for calibration, next first 30 years, then next 20 for the validation. That is normal procedure, but there are some ways are there. Even you can do for the different years for the calibration, like first 10 years, next 10 years like that for calibration. In between periods also we can for validation. It's all data only right, you can arrange what is the way you can arrange and accordingly you can run. Okay, similarly the best way to give the training data is actually normally observed data see right, sometimes there is a gaps will be there, some gaps like for example for a 10-year data is there, last 5 years data is not there for example. In that case that area you should not check for the calibration. Calibration always should be like a continuous data has to be there. So that way you can check the thing. Okay, best way is normal general procedure like is first data you will use for the first 20 years for the calibration or next 10 years like for the validation like that. But there is a you observe data a lot of issues are there, any part you can give for calibration, the remaining part which is there you can give for validation. Why I am saying this one? For calibration what is the important thing? All data has to be there, observed data has to, there should not be any gaps in the observed data. That is the main, that is the best procedure. Okay, so convention is first 30 years or something for calibration, next validation. You want to make it a better means you can go for a different this type of options. Okay, that is SWAT model will allow that one. It will only ask like a which data you want to use like that. So there is one more important thing is there in this model, that is something called warm up period. What is the warm up period in this type of models? Warm up period. So calibration 30 years right. There is initially we need to call something called 1 or 2 years or like almost like a 2-3 years or at least 5 years data we need to use for the as a warm up period. Means it will run simulations, but those things we will not use for any of this analysis process. Since only it is a model is setting up. Since it's a continuous model, right, you can't get initial values correct. So that is like a model setting time. So later you can use for this whole process. Okay. So that are the some of the things we are keeping the rainfall and then doing checking this one like a precipitation on this model. And this is what I am saying is so is like a this is called actually the REA, regional ensemble approach. So there is a technique, that's one technique to ensemble the models by using the weighted average thing that we can do for the ensemble model. And of course we are simulating the flow with those ensemble model data set, and then what we can call as a, this is like a observed data set actually precipitation. So we are using the, it's like it's observed actually, this is a mistake is there, I think this one. So you see here, the goal is only previous case is only one land is land cover we are using, but normal that is not the case, right? So you will have the data set for observed also period also like a land is land cover for different time periods. You see this one 2005, 2018 and 2015 like this, possible, right? And then 2000 you can say the 15 like whatever the data set. So in this what is the thing you are doing here? Normally climate okay, so climate means we can have a future climate models, but how the land is land cover you will get for future? You are getting right what I am saying? Climate means climate models are there, they will give the what is going to be the future rainfall or for every day like that. But how to get the land is land cover for future? It is not so we can say straightforward like a to get that one. So we need to do something, then we can get those things actually. There are different techniques are available nowadays. So to get the future land is land cover. Okay. So one is like a Markov chain. I think Markov chain means is the one type of we can say the running average type of method. So where or it is also called moving average method. So what is the thing is like a, for example, so this particular data set you are seeing, right? If you are seeing each and every pixel, we see this one. For example, cropping systems or whatever things, you will see the what is the change factor. Okay. And similarly, which is the change factor for the like that you can take the previous like a 5 years gap you will take. So each year you will get some changing factor, right? So you will see those change factor, and that change factor you will try to use for the what is the way each one is changing coefficient. Same way you will apply that coefficient for the next 5 years. Okay. So in the first case what you will do, this is the two change years, right? These thing years, right? So these two and in between these two you will get some factor, right? So that you will try to use for the you can say this for simulation of the already existing thing only. For example, you are in 2020. So you will use the up to 2015 or something like a last 5 years data set or last 15 year data set in the Markov model, that whatever the CA Markov model. So you will apply the you can see this technique like moving average, you will get the coefficients. So those coefficients you will use to run the get the climate the land is land cover 2020. So means up to 15 data used and you simulate the land is land cover map of 20. Then you will compare whatever the land is land cover is simulated and what is the land is land cover already 2020 means we have already, right? You will compare. Then you will get some error, right? It is whether coming correct or not. Accordingly you change your model and Markov model or improves. Okay. So once you found fit it is coming correct, same thing you can use for this particular change factors with the coefficients you will use for the future. So 2025, 2030, 2045 like that. It is normally with the this QGIS, ArcGIS, this methods are available. Okay. So there is a land is land cover change prediction itself is one of the toolbox is there. You can get those things. So those related aspects also we are you can say the means there is a one more model called DynaClue, DYNACLUE. So there also there is a different factors are available, like you can say like a for example one industry area is there, that around in some industrial area how it is going to change in the next things. There is called driving factors. So there is like a different ways of giving those driving factors in the DynaClue model. It will give the all possible scenarios. Land is land cover also you make scenario like climate change you are using scenario, right? Land is land cover also like a rapid development, rapid urbanization, so environmental friendly urbanization, like that each of those things accordingly land is land cover will change, right? Those scenarios you can make. So those scenarios you can compare with our climate change scenario. So worst scenario for example nobody following the rules and just like a development is happening. Same thing with land is land cover also, right? That type of DynaClue factors we will give the Dynacube model or Markov model. So I think you are following. I am saying land is land cover, two types of approach is there. In QGIS you will use, that is a Markov model is there, CA Markov model, that is like a technique, one technique to find out the future land is land cover. Okay, and there is one more concept is called Dynacube. Is a one type of model where you will give some factors in the each and every land is land cover, and it will give the future factors. So those things you will apply back in the model, and then you will get the land is land cover changes. No, Dynacube is not in this. Yeah, the cellular automata model with the Markov. Markov means they are combined these things. CA Markov model combinedly they are, you can say, made some of the techniques like how the future those things we can make. That's the thing. So since all this CA cellular automata model or whatever the model, we will always depending upon the present scenarios and then back these things. You just only the factor, some factor will apply. But this Dynacube model means we can have your own control will be there, that is change factor controls will be there. Accordingly we can change. Okay. So those things you can check and then you can make. Yes. Okay. So like this, so with those things we made this land is land cover model. You can see 2030, 2050 and then this like this. So you can make this type of this thing. This is the CA Markov model we used actually. So here after those things, now in the your SWAT model, right, we have to use the SWAT model combined land is land cover. So for example SWAT model you are building also, there is a SWAT model land is land cover input you will give, right. So that there is one options are there, SWAT model you check actually, land is land cover base you will give, then you will give the next, for example during simulation itself. So next 50 years for example time, what type of land is land cover parameters it has to take, that we can provide. Accordingly it will simulate the, so land is land cover plus what are the climate parameters, accordingly it will simulate. Okay, so you can see some of these things like a we made a like a few these things like a precipitation RCP 4.5 scenario, and then this one stream flow the simulations. This is for the historic, you can say the period. Just you can I will show you the, yeah, this contain the, you can say both the things. You see January 20 means to the future period actually. So 39. This is called first future period. This is the second future period 2041 to 2069. This is the third future period, like 30 years. Whenever you are applying for this climate change models, right, normally future we are divided into different zones, means time periods. That is called normal way of doing is like a normally climate model data is available for 100 years. People will do as a three things, three periods: first future period, second future period, third future period, like that. They will also call near future period, mid future period and far future period. That's the way they, that is a standard practice. So sometimes people only do for the next 10 years, next 15 years and next 20 years, like that. That is also possible. So there is no logic like for example some parameters, for example evapotranspiration. There is no logic to understand after 100 years what is going to change in the evapotranspiration, right. It is very important like next 10 years how this evapotranspiration is affecting. That is very important for the irrigation other practices. In that case only near future is sufficient for us. Accordingly we will build our models or build whatever the we will do for the near other things. You are getting some stream flow, those things means like a longer, some water source planning you have to do for a particular state. In that case you may think of like a bigger future periods. Got right? That okay? So these are all like, of course you can see like a lot of simulations like increasing, decreasing, those all the things are there. But more interesting thing like whenever you do for this one it is okay, but we can always check for the months actually. So 12 months are there, like most times it will get a very long duration data set, right. It is like you see for the, for example 12 months in the future, first future period, January, February, March, like that, each month what is the available water for different things, as a groundwater, as a infiltrated water, or as it is a surface stream flow. That is more interest for us, right. So for example in the month of July and August, how much water is available for each month in the future. That will tell us so many things for us, right, how to make agriculture practice, our things. So you will show, I will show you some places where really there is shift. For example, normally water has to be available more in the basin, in the, for example, these basins, southern Indian basins like a Krishna, Godavari, water has to be available in the August, right? August or something, September, like that. Sometimes we will see shift. They are shifting toward the July or shifting toward the September, October. That is because of the change in the, we can say, weather patterns or climate change, these things, is shifting those things. But all information we will get here. Okay. So some of those things we observed. Actually, this is the way to do the things. It is called actually the comparison. So baseline, and we see the scenarios. Baseline means like a same thing. This is also we will do with the historic data, and we will compare. So you will do this one, then we will get an idea like what is the present case and what is the future case we are making. And you remember here when I am baseline I am checking, I am not checking with the observed data set. Since observed data historic, there is a one factor will be there. Observed data and historic. When you are comparing, we need to compare the historic and future. So what is going to be the value change? Okay, then we will get whether the really for each thing, for example, in this case you see, there shows that water is available more. So sometimes it may show like a, you see in this case, something like a, everything is available more you are seeing when compared this one. Sometimes you may get like a, it is available less. But all depending upon the type of scenario you are using. Okay. So this one you will like a small basin, right? You can see like a little bigger basin, like a Krishna basin. How we will see these things. That's what is the thing. And it is also like a very important like a inter and intra-annual. Inter-annual means what? Just now I told, right? Intra-annual means within the year for a monsoon, non-monsoon. Okay. So pre-monsoon, post-monsoon. Like that within the year, over the years, within a year how the things are changing. That is called intra-annual. Inter-annual means like a whatever the I can see years, like a between the years, like a next 10 years to next 20 years, how it is changing. That is called inter-annual. That way we can make analysis. Of course, this is a what I am saying is like a, how to make an ensemble database. So this is a thing. So you can see like a, we tried for a bigger basin like a Krishna and like a Vardha, like a one is like a very big basin in the sub basin for the Godavari, like a there in the Maharashtra maximum basin actually. So these two things we made, like these are the I am saying the climate models. Just like I will show the data set since it is already same, what I am explaining is same thing repeating. So that's why I will show you the things so that we can quickly conclude. So these are the different models. This is like a model name. For example, community climate system model. Like a, it is like a different organizations, different countries. Every country have its own model actually. They have their own model setup. So they will run on some computational system and they will keep the data set. So that's why. So whenever you use, it is always like a mention their clear models. What is the models you are using? So somebody asked question like a which 5 model, the questions always in the climate change studies, which 5 models to use. Already I told, right, what is the way to get the selecting the models. Okay. Then you can say the scenarios also, like one is like always better to say one normal scenario and one worst scenario, it's always better to run. Okay. So here this is the, you can say the how to make a ensemble average technique actually. So this is like a, both the things you make the ensemble, this is what I am saying, ensemble weights. So then ensemble weights to the variables of the climate models and then we will get the ensemble historic and future actually. This is the way you can do. So this is the just like we made a some small thing in the for this Krishna, you can see for this Vardha basin actually you see here. So normally you see the before this is like you see observed and then this is like you see the simulated, you can see here observed data and simulated, right, model data set. So if you are not doing the this right like this bias correction, right, they will not fall, like they will, we have the variations. If you do means they will maximum they will match actually. That's why always better to do the bias correction. Then only we can get a correct. You see this is like this curve you see trending towards observed, right? It is not like it should be like a pass through middle, right? Like a both observed and model is perfect means what? It's like almost like a 45 degrees line, right? Like this, right? So if you do if we didn't do correction, for example, what is the meaning here? Most of the data is towards observed. And there is a bias is there. So if you make this correction, it will almost like a come to the middle. That where the bias correction we can apply. So there are so many techniques are available nowadays. Most things are programs are available. We can see which is the best correction and we can apply. normal something called quantile mapping, like that. So many techniques are available. So you can see more about those things. So this is the I am saying SWAT cup model. Just you can quickly I will show you the how. This is the I am saying two important parameters we want to check. So just I will run these things same. So previously we are checking at one outlet. Small means one outlet is sufficient. At Krishna means so many gauge points are there, right? That is called multi-site calibration. You can do this multi-site calibration, and so that it will give a better simulation actually. So multi-site calibration we can do, means at the outlet and different other positions also we can do calibrate the SWAT model. So that's what is the thing actually. So these are the other places, and these are the, you see, this is what I am saying. Always you see this thing. So all the literature, if you see, it should be like a minimum more than 0.5. This R square and NSE, and above 0.75. Above 0.75 is always better actually in the calibration, and people will accept validation. It is somewhat okay. You see, this is also okay, but calibration you need to get little more towards above than 0.75, and then this is like above 0.5. So we have to try like that many simulation, that way the changing with the thing parameters. So these are all the things, but these are all like a scenarios, like a each month, like a monthly. What is the, so one observed will be there, remaining all like a scenarios. So main I am interesting point is, you see, over the period by different models, whether the shift is there. For example, something is happening in the somewhere in the July, August, right? It's shifting means there is some issue in the future. That's what is the thing it will provide. So this is like a, somebody want to do that inter-annual and intra-annual. There are some established steps are there, means equations. People can apply and they can check these things. So this is the what intra-annual and these things. So what is the coefficients available for each and every period, how much variation is there. So more the value means more change is there, it will tell. Okay. So these are the intra, right, inter-annual, like each you can say the model like a inter-annual, what is the variations are there. So this is like a more the value coming means there is a more variation is there. Normally RCP 8.5 model you will see the maximum variation. So it will give a, to the present, to the future, how much variation means more the value is coming means, you see, more the variation is there, means more the problem, like that. So of course these are all the giving a different models, all these things. So there's like a more like explanation of the all these things, but we are more interested in like whatever I am showing right now. I will just quickly show these things, but you are more interested in these things. Okay, these are the all the components, evapotranspiration, these things, they all will tell you a one guidance for you as what going to be the future thing. That is more important. Okay, this is historic saying with the future. So you see all these numbers, when you see the previous one and 800, right, you see most of those things in the future, some parameters will be like a more than, we can see how those things are varying with the various models actually. And of course second and all other future periods, so is like a same like I am saying before and after bias correction, these things. So this is more interested actually, means we can see this all those things like a like interpolation techniques. Some yesterday also we are trying on these things in the QJs, right? So this will give you the idea like a spatially how things are happening. For example, historic like this is the precipitation is there, is going to be changed something like this in the picture actually, that what will give actually. So it will give a complete picture idea like all the things. So like this all things I kept actually, we can already shared also this presentation already there with you PDF copy in the drive. We can check more these things. Same in the feature you see how these parameters are there. In the we are showing for 8.5, you see it is like a means more color changing, like you see that scenarios means the problem with the availability of the rainfall is like a, especially rainfall availability is like it is saying something like increasing in the, some of the areas, the feature it's like that. So similarly the I can say the monsoon, only monsoon if you take, so across the basin we can get how the things are happening changes. So that's all like some of these things. So these are all like of course parameters, all these things are, I will just only one thing is like here you see the things for the present, and then future is like different places, all the dotted lines they will tell about how those changes are occurring. So anyway, this is the overall thing like climate change means what is the best. So you can use the SWOT model and you can do lot of things, present, future, all the things. So only thing is your study has to end with adaptation, and uncertainty is very important to study. Like you tell, I am simulating, my simulation may contain 10% error. That in a position you are in a position to tell that one. So I said right, it is like a long series of, you can see the literature which we done actually, our group along with our Sridhar also, like we work lot of things. Everything available in the public domain. You can get these papers. Most of the time some of the easily, they are not even the general open source publications. You can get these things and then you have a look at those papers. Give a lot of idea, like whatever I am saying, everything is you can get. Yeah, that's all from my side. So any questions from your side first? So you got understood it, like a simple climate change, like a study we want to make, means how we can do with the thing, and then some of you are saying like you are using SWOT model, so you will get a complete picture. SWOT model means how we can make a climate change study, SWOT model data sets. Land surface temperature you can't give directly, but you can give as a maximum minimum temperature. Only it will take the input of, like there is a weather one like different inputs. One is like a all that dam, soils, land is land cover. Then other is like a weather. Weather normally contains so many parameters. In that rainfall, maximum temperature, minimum temperature. They are the main thing. Solar radiation, relative humidity. So many, like some almost 10-15 parameters are there. But people will give only these 3 parameters. So LST you want to convert into maximum minimum temperature. There's some nowadays is available, some of the things actually. So for a point, grid point, you can check up giving those things. Since LST you will get from remote sensing, right? Remote sensing you are going to grid point, you have to see. Okay. So you are asking question means okay, otherwise I will always ask question quickly. So this one you will tell actually, you are asking like where we can get RCM data for our Indian region. Just now we discussed in the class, right? Cortex scenario. What is the organization? IITM, Indian Institute of Tropical Meteorology. So if you go that one and simply you click, they will see the entire thing. In the first day class, one of the that screenshot is related to that only. There I gave that you can say web link also. You can check actually. So you can say we can use the SWOT model. That's the thing actually. Bias correction, downscaling. I think there are 2 different aspects. Sometimes people will confuse that. So that's why just I will tell you that we will stop. What is the difference between bias correction and downscaling? Area of interest, not only downloading is different, and downscaling means they are available in 1 degree by 1 degree. We are downloading from 0.1 degree by 0.1 degree, 0.5 like that. That is a downscaling. Okay. So then bias correction means you are correcting the downscale data with respect to observed data. So historic model data will be there, right? So you are downscaling that, you first of all do the bias correction. Okay. So in the bias correction, what you will get? Bias correction factors you will get. So when compared to the observed, what is the historic model? Everything like temperature, rainfall, you will get the coefficients, monthly or daily coefficients you will get. That with that you have to correct the future data set. So that is a bias correction. Weights you have to provide. This is very important. People will sometimes they will confuse between these 2 things. Downscaling, bias correction are 2 different aspects. Sometimes you have to, most of the times you have to apply 2 things. Okay. Yeah. So ensemble I told, right? Normally ensemble is the best thing to use, not like a single model. Okay. So single model will always say there is error, right? Each model having error, right? We will make at least averaging, or you will use the combine the things with weightages, you may get better thing. Or you can't make 100 models different, you can't study. Better to make one ensemble value, then it is more easy for us to understand things. Okay. So I will stop at this point, then I will hand over to Sridhar with a gap of, we'll give 5 minutes gap, 2-3 minutes gap for them. Yeah. Yeah. Yeah, we will give you a 5 minutes gap. So now it is 10:30. Snacks available? Yeah. Then I think we will break for 10 minutes. Yeah, so 10 minutes we'll break for the snacks. Then Sridhar will continue the next 2 hours with a gap of 5 minutes like that. Okay? Okay then. Thank you.
You had a wonderful first hour talking about climate change impacts, looking at the modeling. That's very important, very hands-on. Those who want to really expand, your research, taking cue from there, I think it's helpful. I see a lot of interest in talking about the sources of data, downscaling or bias correction to calibration, all of those things. I think they are very important, and if you want to do the modeling correct, you need to really understand those steps. Of course, it's not something still bringing novelty to the work. That will be a challenge for you if you're trying to replicate what is presented, right? What I'm saying here is, if you try to understand what is presented, you have to go one step further, because they will be saying, oh, you have actually replicated the work of somebody that's already done. Maybe the only change is your watershed, or maybe a different time period or a different model. But basically, when it comes to publication, what happens is, there is a basic question people ask, which is, what is the novelty of your work? Tell me what you found out that nobody has found out so far. You have to keep that in mind. Certainly taking the first step of understanding what's done, how it's done, is very important. But what I'm trying to urge, what I'm trying to emphasize, is that you need to go one step further from the point where you see the literature has actually showed you the way. Okay, so understanding is very important. That's what you're doing here. So with that, I'll stop. Of course, I have to have this disclaimer. I think what happens is, we are talking about advanced modeling, all these techniques, right? And then going back to fundamentals again. So there is a kind of a seesaw approach here to everything what we are talking about. But it's also a check for us to understand whether or not we know some of those minute details about hydrology, because I'm trying to bring everybody on board. There are some folks coming with some background, but some do not have that background. So from the beginning, we are emphasizing that we will start at a level where everybody feels comfortable. There may be some redundancies or duplications or repetitions, so please bear with us. Just take a relaxed mind to really watch what we are talking about, if it's known to you already, or you are welcome to contribute. I also brought this plant that was given to me on day one. There is a reason for that. I will bring that when we are talking about some stuff today. Okay. I'll go with first this precipitation, because we as hydrologists, I always emphasize that precipitation, which is the main source for any analysis that we do, right? So that we need to really understand different terminologies related to that, how it is partitioned. There are minute things that we need to understand. It's a bulk transfer process, right? Basically what I'm talking about is that liquid that sits in the cloud, once it's not possible to hang on to the cloud because of the weight, it condenses, forms as a big droplets. Once the size grows, it falls as a bulk volume or a quantity, right? That's the bulk transfer process, that what we are talking about. Unlike the diffusion process, which is like evapotranspiration or evaporation, it happens for these plants on a daily basis. But do you see, like how you see precipitation? When you see precipitation droplets, you know that it's falling, but you don't see what's happening with respect to evapotranspiration, because this water vapor flux that's actually diffused into the atmosphere. So that's the difference. So there are some terminologies like that you need to understand: diffusive process versus bulk transfer process. When we are talking about precipitation, I think yesterday also we emphasized this amount, intensity, and the space and time concept is very, very important. And it's a blessing in disguise for us. by the way of saying that space and time distribution. It is not uniform, right? If the rainfall falls uniformly over the whole region, we don't have too much of work to do, right? Everywhere it's going to be greening up, everywhere it's going to have the same hydrological process. You can really understand one place and scale it up for the rest of the areas. All of those simplified approaches you can take, but in reality, in nature, you don't see like that. In some places, it's heavily dense vegetated areas versus barren soil versus slopy area versus flat area. So you have all these distributions just on the physiography side, but when it comes to precipitation, it also falls very, very differently in different places. Snow versus rain, even within the rain, there are different magnitudes that we are seeing in different times. Some places get in 1 month more, some places get the other month more. So again, those things we need to quantify and use that for our understanding and make sure that we are using it for making decisions based on those, right? So presence of vegetation help absorb some of the impact of raindrops and reduce soil sealing. So vegetation really helps in minimizing the shock from the raindrops that falls on the soil surface. In precipitation literature, another terminology people use, which is called probable maximum precipitation, or PMP. Very common terminology, of course, used by WMO, World Meteorological Organization. It's a theoretically greatest precipitation depth for a given storm that is physically possible for a given area and time. So they set certain number for every location based on the climatology, based on the atmospheric process, based on the transfer of moisture from the neighboring area. So you can say for every place there is some amount of magnitude or magnitude of precipitation that's going to be the uppermost limit, and that's called PMP, and that's primarily used for engineering design calculations. Both, it combines physical and statistical attributes to that. We are trying to really understand combining both of those two. When I'm talking about physical, how much rainfall we get, and based on every rainfall event that comes through that area. Plus there is also some statistical analysis of whatever extreme events that we can consider towards that. There is some kind of uncertainty. When I'm saying statistical analysis, in addition to physical magnitude, you also have some level of uncertainty associated with those amount of precipitation that you get. People combine these two as a theoretical quantity and come up with some safest number that you can use for high intensity or need for designing certain things like dams. Now when we talk about precipitation, just when it falls on the plant or tree, like this is not the purpose I am trying to show here, but I am saying assume that this is the tree that you are seeing here. Okay, when the rain falls on it, some of it falls on the leaves, they stick around, they don't fall, right? And then they are called canopy, right? This is these leaves, engineers, right? So I'm trying to really explain biology and botany here for you guys. Okay, some of you are geographers, so you have some background. Leaves, okay, they actually intercept, or canopy, they leaf or canopy you can call, and then some don't really fall on the leaves, right? Some fall on the stem and then flow through, and through fall, basically the gaps that you have between these leaves, when the rain drops on them, directly falls on the soil. So there are simple things, right? I mean, we normally ignore all of these smaller details, but when you are for a single plant, how the rainfall falls and how it's partitioned doesn't matter. But think about big trees, full of trees over a large area. The intercepted precipitation on the canopy alone can be a big number. You cannot ignore it when it comes to flood calculations. That's an important part of it. That's why I wanted to emphasize on one aspect of it, but I will come back to this plant again. The purpose of course, showing all this is to relate to another example. the place where I come from, where you ask a kid, where does this milk come from? They immediately say it's coming from Walmart. They even don't know where it's coming from. They see only the can, and can is the cow for them. Basically, they say, oh, it's coming from Walmart. They even don't know where it is coming from, right? So I want to really connect real world by giving this example. I know you know this, but still keeping that concept, plant is not same as the tree that I am talking about, but as a modeler, you need to know, you need to associate the real world into your consideration. So the same thing that I am talking about. So the amount of water that's actually falling on the plant is evaporating or evapotranspiring, but the partitioning that I am talking about, I will come back to this again. Canopy interception through fall means that actually falls in the gaps of those leaves, and then stem flow means it's actually falling on the bark and then reaches the root and it gets into the soil, becomes infiltration, right? Those are the terminologies. Again, I think these numbers really are important, and people, I mean, mostly empirically they derive, but there is no way of collecting this data. So when you are getting precipitation, it's a simple number, but even if we don't appreciate what that number means, how they get, you will not be able to really relate to other processes like this. That's why I am saying plant surface retains some water, which is a function of plant canopy, like I said, depending on the leaf. If they are big leaves, banana plant for example, it can hold a little more water than the small ones. Conifers, like the thin needle leaf plants, don't even hold any moisture. So depending on the vegetation, the interception happens, right? So depending on the size of the leaves. Again, if they are big trees and light drizzle, that's your umbrella, right? You go and stay underneath until the rain stops if you don't want to get wet. So interception allows plants to intercept the falling precipitation. That is the meaning. And of course, it varies with the type of leaf, size and shape, and leaf density and arrangement. And of course, rain intensity, what kind of intensity the rain falls and the duration and wind are more important for the interception process. And again, nighttime versus daytime, and also the seasons matter. In India, of course, seasons to some extent matter, but in the northern hemisphere, it's much more important. And interception storage, that's another thing. Water holding capacity of the plant surface is limited, which is a function of season, antecedent moisture on the plant, interception capacity, right? So these three small things, right? Like we can say season. Why do I say season? There is also, now it's spring season or summer here, Vasanta Kala, right? Whatever it is, or after spring, it is now fully bloomed green plants. But before that, you will only have stems, right? Or in the northern hemisphere, we see all the trees are like, only barren, tree or senescent trees. They don't have any leaves or anything. When the rain or snow falls, it directly falls on the ground. But now with all the leaves on the plant, it may not. And then the interception capacity changes based on that exponentially until the infiltration capacity is achieved. Basically, it may not even go to the soil, right, when the interception happens, and it will increase as much as possible exponentially, and then once it starts falling, it will start the infiltration capacity and maximize up to the soil that it can hold. Interception storage capacity is equivalent depth or expressed as an equivalent depth per ground area. So we are talking about drawing an equivalent area and see how much flat leaves that you can stack on it. So you can calculate the ratio based on the biomass that you have over the flat area that it covers, right? That is the amount of water that it can hold. Normally they consider 1 to 6 millimeters, and highest in coniferous forests, basically interception storage. So this number, it might look smaller, but in a short period rainfall, when there is flood producing event happens, this number can be an important one. And also, in a big forest canopy, you have second layer of plants they call understory vegetation, right? They also store water. It's not just one single tree. If you walk even on the campus, there are big trees, there are small trees, there are bushes, there is grass, all of those layered stuff. So those understory vegetation can also hold water. So interception storage is subjected to evaporation. So the water that sits on the leaves, as soon as the sun comes, it starts evaporating, right? So that's the first source of supply of moisture for evaporation, only when the canopy is wet. And interception loss occurs in addition to plant transpiration. Basically, they also evaporate in addition to plant transpiration. So they combine both together. Higher evaporation rate from wetted vegetation, which we know already, and aerodynamic resistance is only causing interception loss. So will not get into the details, but there are energy transfer, aerodynamic transfer. So the aerodynamic transfer happens with this interception storage. Energy required for higher evaporation in forest is provided by advective energy. So now one thing is to be known. You have vegetation, right, on the ground. In forest, there are lots of vegetation. You have plenty of moisture in the ground because of the rain, but you need energy to transfer that water into water vapor into the atmosphere, right? So that's where we probably will limit energy limiting factor for evapotranspiration. There is water limiting factor for evapotranspiration, energy limiting factor for evapotranspiration. What do we mean by that? When you have plenty of energy, but the soil is dry, there is no rain for a month, plants are already suffering, at that time your evapotranspiration is not going to be at the higher level. In the same other context, energy limiting condition means you have plenty of moisture. On a cloudy day like this, you don't have sun coming out, you don't have energy supplied to these plants. So the advection, the energy that's coming sideways, moving from the circulations, moving from the neighboring areas, advected energy can also help them to transpire, to evapotranspire. So the interception storage actually is lost in many different ways, as much as water is available. Okay, so temperate forest has got modest interception storage, but wind exposed forests have higher number because they carry this energy from the neighboring areas. Grasslands have some modest number for interception storage, and again these numbers are really making a big difference if the homogeneous area of some of these vegetations exist. Through fall in the rainfall is the rainfall that reaches the ground that I was talking about. Stem flow is the one that is moving through the stems, right? And then it's a function of the size of the tree. Big trees that have a bigger trunk will really have water moving through. Smaller ones will have a smaller quantity of flowing down to the soil. Substantial amount of moisture is sent to the base. So the lesson is, of course, you think when we see precipitation, it's going to run on the ground, right? It's not. When we have vegetation, there are so many other smaller things that happens before we see that rainfall becomes runoff. That's why I'm trying to break it down into all these smaller things. Now you look at this graph or schematic where it shows all these things, right? What we talked about: precipitation, interception, infiltration, surface runoff, through flow. Oh, another thing, through flow that I did not mention, I think probably in the previous bullet. Water actually can flow on the surface, water can flow also beneath the surface, the one that parallel to the surface depending on the slope, right? So the bottom or the lateral flow or through flow that we call is also important. It contributes to base flows in the shallow streams. It can also directly end up in the ocean. So what you see is not the only one what you get as runoff, right? This big, we all know that. But in runoff calculations, there is surface flow, subsurface flow. You also have deep, discharge, which can also connect with this aquifer and then go into the groundwater discharge into the sea. So many ways water winds up into the river, into the ocean. So when we are trying to model this system, are we accommodating all of this? That's a question that we want to be asking. So we talked about uncertainties just now, right? So why are we not able to predict using a model? You are going to do stream flow simulation this afternoon. So we are actually going to use simple model HMS. You will see all these processes are kind of bundled up in a simple formulation. But if you want to go deeper, there are options available in HMS that you will appreciate by knowing all these things. Wow, if I ignore these processes, can I get my runoff correct? You know, that is a question that you should be asking. So you cannot use the model as a black box. Okay, that's one important quality or characteristics as a modeler that you should cultivate, which is trusting the model, which is not good, which is not correct, right? You should always have a doubtful approach to that, because you don't trust it. You know, they are useful, right? Models are wrong, but they are useful. That's the normal way of saying. They are wrong, you go with that assumption, but they are useful because they give you some numbers, but you can play with and modify depending on your understanding of the system, depending on your understanding or how meticulous you are in defining the parameters you want, right? In modifying the code that you think that would represent your watershed. You know, SWOT, HMS, WIG, any number of models. If you think, wow, I am successful in running the model, yeah, that's well and good, that's the first step. But do you represent the characteristics of the watershed that you want to simulate? Then you look into all these things and try to answer, okay? I think I'm going to skip all this, I guess. I think I explained. Capillary force and gravity force, you know, that is one thing that you need to be thinking about. I know you probably have some basics on that. Capillary force, soil column is there, right? In this, let's say I will take the same thing here with this pot. I don't know if I can pull out the soil from here. Yeah, I think so. Right, this is the soil column, right? I watered this for the last 2 days because it was dying. So the plants were wilting, so I had to water them, and I watered, so it's pretty wet. So what happens now is basically the pores that are in the soil column are completely filled, right? They are completely filled. So there is less capillary force effect on this because I already saturated. But when they are dry, these voids or the gaps that you have will have suction associated with that. It will pull the water through those voids. So that's the capillary force that I am talking about. But now, since I saturated it, I put water in it, it's going to flow through, right? What I am saying here is basically when I put water, I put all this tissue paper because my table was getting wet in the room, but then there is no pan here, so I'm kind of having some difficulty in holding it. So look at this. It's not much water that I put here, right? So just a sample quantity that I put, and it starts dripping already. So this is the gravity flow that I am talking about, right? The soil column cannot hold. Even I probably put 2 teaspoons of water and it started dripping already for a soil column of a small quantity. What does it mean? What does it mean? The water holding capacity of the soil already exceeded the limit, right? So it started dripping. I don't know whether you could see the dripping that I showed. So it was dripping already, right? Small quantity of water that I apply, saturated column is already dripping. So we want to integrate this not for one soil, one plant. We want to integrate this for the whole canopy or whole landscape, whole ecosystem in a model, right? Anything that is not held is coming down, flowing through, reaching the groundwater. That's what we are trying to do. So the process is complex. We cannot simplify that. but we have to simplify to get a better understanding. When I say models are wrong, but they are useful, that is the meaning. You can still simulate and get some numbers, but you have to always go with the suspicion, doubtful eyes of questioning or asking whether or not you can trust those numbers. Okay, so thinking about uncertainty through statistics, programming, coding is one thing, but thinking about uncertainty with respect to process, you have to put your mind and head into some of those processes like what I am showing here. I hope I make a case here to make you realize that don't close your eyes when you are modeling just to say I want to hit it running, and it's an excitement. As a student, when I was doing, my first job is to make the model work, make it run. When I get the results, I am so happy. I don't care whether the model produces the right result or wrong result. Probably you have the same feeling, right? So now that is the first step. But the next step, as a mature person or matured scientist, that what we should be asking is to ask whether or not we are representing these things in the model correctly. Just the part gives us all this information for us, right? So I'm just, this happened to me this morning, this, Einstein moment of thinking about why not I show this in the class, because these, leaves were wilting, hanging down, and I saw that they were dying. So I thought maybe, it's not holding much moisture, so I had to feed water. It's like feeding the baby. Every 2 hours I put water because they don't have big stomach. Depression storage. Okay, so what happens when precipitation exceeds infiltration? Ponding occurs, right? So initially when after all that soil processes that I'm talking about, now we need to also quantify these potholes we are really familiar with, right? Any place, any country, any continent you go, you will see potholes, holes everywhere. When the runoff starts, you will first see them getting filled up. That quantity you need to estimate, right? This retention of water in micro depressions constitute depression storage. That's a big quantity, 3 to 13 millimeters roughly. Evaporation and infiltration can also take this moisture away. And then another storage component that I am talking about is soil moisture. Greatest proportion of soil moisture infiltrates, or water or precipitation infiltrates into the soil, right? Except intense and long duration storms. When strong storms comes, of course, soil moisture quickly gets saturated and then the remaining starts flowing right away. Otherwise, infiltration is the biggest process. You are going to see in the afternoon class today, there are varieties of ways you can simulate how much water is percolating in the soil column with HMS. SWOT has the same options also, green amped method, other approaches, Horton's equation, Phillips equation. So there are so many formulations people have come up with, and you are going to actually appreciate how much is important. Soil moisture is important not just for floods, it is more important for droughts. So I want to emphasize that with this plant again, that how much moisture that we are having in a given soil column is dependent on the size and shape of the pores and the tension forces that I just explained, capillary versus adhesive forces. And then this part is also another important thing that I think I already demonstrated with this plant. Field capacity, which is, I think, probably some of you are familiar, those with geology or soil background, and civil engineers also, of course, natural resources engineers, I'm not sure, you must be having some soils background, hydrology class. Field capacity is the soil water content of soil profile when gravity flow of water from soil matrix is negligible. I'm just reading from the slide, right? So I put water, it started dripping right away, right? Before it started dripping, it held that water, right? Before the gravity influenced it to go down. So that amount of water before the first droplet comes out is the capacity of that soil column to hold the moisture, and that's the field capacity that I'm talking about. The amount of water that's held by the soil column before the gravity flow starts. That is the actual volume of water that is held for the plants to use. Again, for well drained soils, field capacity is the upper limit. For a sandy soil, of course, it does not hold too much moisture, right. Field capacity means, of course, when you put some water, it is going to stay there, but any amount of it will be a small quantity, that will be the minimum quantity that is available for plants. That is why you do not see many plants in the highly drained soils like sandy soils. Wilting point is another one. I mentioned that the leaves were drooping, right. When I mentioned this morning, when I saw this, it was all hanging down. So I did not like it. So I saw that it is reaching that point of going to ICU, of putting to the clinic, of supplying moisture. So wilting point is a point where the plants are almost dying. You do not want to go beyond that point, otherwise the plants will die. So it cannot, it does not have energy. So that point you are putting IV for people to really get up and run, right. So the same thing happens. So the amount of water between field capacity and wilting point is the quantity that we have right now. Right now, what the moisture that we have, it does not drip, it is also not wilting. The amount of water is the difference between field capacity minus wilting point is the amount of water that I have, roughly about 0.3 or 0.4 I would say for this soil. It is about red soil type, it is not heavy, it is not highly permeable soil, but it holds about probably 0.3 to 0.4 cubic meters per cubic meter of moisture. So this soil moisture is a fundamental part for dividing runoff, precipitation, and also used for drought calculations. So have some understanding of this, that's helpful for you, when you are talking about, I know some of you already talked about modeling drought, right. When you are talking about modeling drought, this is a fundamental thing that you need to pay attention to, like what we are trying to do here with drought. We will build on this based on available moisture, then we will talk about different types of droughts. But when it comes to understanding what it is, then you will probably play a big role in enhancing the understanding. Redistribution of soil water due to capillary flow after gravity flow ceases. So basically, when the gravity flow stops, right now, there is no gravity in this column that I applied. So there is some kind of movement within the soil column is happening. There is some push and pull that we do not see, of course, but I am saying that there are options for soil moisture to move from one place to the other. Probably I am belaboring too much on this point here, but I will kind of use this to skip for now. Overland flow. Now, having partitioned precipitation after allowing the plants to take some, allowing them to infiltrate, and then storing in the soil moisture, the remaining goes as runoff on the top, on the surface, right. And again, we also talked about depression storage. All the holes have to be filled up before the flow starts when we calculate the actual runoff. But there is a terminology called sheet flow, right. There is a terminology that is very shallow water with high velocity, or overland flow, where in urban areas that we normally see. It depends on rainfall rate, infiltration rate, the slope of the surface, and then any obstructions that you may have on the roads. Again, in urban areas, this is pretty common, right. You might think, okay, this does not pose a problem, let it flow. No, actually, when you think about large, impervious areas, this amount of water can be significant, and with that velocity that it produces and the time it finds to reach the stream, nearest stream, and then reaching the flood stage can be really fast, especially when the rainfall intensity is high, right. So that's what we need to be worried about when you think about overland flow. Hydrology models do a good job of calculating overland flow, but I think many times they miss all the smaller things. So they end up relying on some of the hydrodynamics models for coming up with velocity calculations, both on the land surface as well as inside the streams also. And then humidity or in humid regions it's not really significant unless the soil is saturated. But in semi-arid regions and arid regions, like you saw flash flood, right? I showed you bone dry soil was there, and then suddenly when the rain comes, the soils cannot really absorb that water very quickly. Sheet flow happens. That sheet flow, here in this context we call overland flow. It could be flash flood producing flow also. Through flow or interflow is the one that I talked about, like parallel to the surface but beneath the surface, right? It happens because the hydraulic conductivity, horizontal hydraulic conductivity is higher, way higher than, many times higher than your vertical hydraulic conductivity. There are two terms I am talking about here. Conductivity, hydraulic conductivity means, flow of water through, the gaps, but it can also move horizontally, it can also move vertically. That horizontal movement is way higher for through flows, because that's the reason why you are seeing that lateral flow happening than the vertical hydraulic conductivity. Mechanisms of that includes the Darcian flow, unsaturated Darcian flow in the soil matrix. Darcy flows, I don't know whether you are familiar with. It is a function of the elevation or the drop in the head over the distance, small distance or short distance. Preferential flow that I talked, I did not probably talk. If you see in this graph here, you see these rills, these are called rills, right? So the water actually preferred to go find some incisions they made. They started entering into the subsurface and then end up into the stream. But this rills really becomes big over time. But I'm sorry. So that preferential flow that I am talking about in macropores form routes that largely bypass the soil matrix, and you will see them clearly in some dry areas. I was witnessing in one of the deserts where I happened to see the rain that was dropping, and it made like a pipe flow that was happening, because of the preferential flow that it, the soil, matrix collapsed and it created like a pipe flow. Water drains vertically below in the groundwater system and reaches the deep aquifers, and that is also another important, precipitation partitioning component. This, geology, I think I am going to talk about groundwater in another slide also, where they store large amount of water and transmits, whenever we need it, or pumping them from these aquifers. Let me actually show that graph and explain this part. Groundwater recharge is a seasonal phenomena. Basically, it's a slow process, but it happens over few weeks to months. It's a seasonal scale. It is not a fast moving overland flow that what you would see. The residual quantity of remaining precipitation is allocated as surface runoff after allowing this groundwater discharge. So these three parts, of course, are big in number, but groundwater storage can be smaller in number depending on the geography. But let's actually ignore all these bullets here. Just focus on this. So what we are talking about here is, for those who have geology background, will not have any issue of what I am talking about here to understand, but for general purposes I have to explain this. So this is called aquaclude, right? They are hard rocks or clay pans, two layers that are formed. Water is actually trapped in the middle of those two, hard, impermeable, nearly impermeable surface. That's a confined aquifer. This is called confined aquifer. Anything above that exposed up to the top surface is your unconfined aquifer, which also has the atmospheric pressure in them. Basically, it's open to the, if you put the well, you can see the water level here, which comes above, near the surface here. So here what I am talking about is A confined aquifer, if you pump water, of course you get some amount of water. Unconfined aquifer, apply water, discharge happens. But it is a function of specific yield, how much water that it holds and how much you can extract. That's the ratio that we are talking about. As specific yield is one of the terminology that people use to say how rich is your aquifer in terms of supplying water for discharge. And this is a big component in some places, but not always. But it cannot be ignored. And people, groundwater hydrology itself is a big field. When it comes to flood studies, it's not a big deal, but there is some amount of water that's lost to groundwater aquifer that we need to account for. That is a loss when it comes to calculating the runoff. Sure. Yeah. Confined aquifer should be higher, right? Because you have the potential. Whatever, I mean, it's a ratio of amount. What is specific yield? Can somebody tell? If anybody knows it, what is specific? Sorry. Yeah. Uh, no, actually, I would define it like this: the amount of water that can be taken available for extraction over the total volume of water that exists. So that means they are not the same. For confined aquifer, let's assume that you have a container, okay, you have a container, there is nothing to stop that water to pump other than the walls that are really holding it tight, so you can extract everything out of it. So it's a high number for specific yield for a confined aquifer. I don't know the exact number, just to answer the question, but it should be higher than this. It's 0.7 up to, I think it can go. But the other ones are smaller because you have push and pull, capillary force, gravity force, and all of those things come into play for unconfined aquifer. Normally they define that for unconfined aquifer. Yeah, but I am actually bringing this to the basic slide, which I show to undergraduates in hydrology class. But I wanted to show because we have some audience here that would probably benefit by talking about different components of hydrograph. And you are going to simulate this today, and without knowing this, different parts of this, it may be difficult. So I'll start talking about this. So there are different things here, right? This is a recession limb. It goes up and then it comes down, right? So a couple of things that you see here. This is the amount of rainfall that we get. So notice here I call net rainfall. These are terminologies people use, or rainfall excess, net rainfall. What does it mean? I want your participation here. What do I mean by net rainfall? Very good. Amount of water that's available after accounting for all the losses. You remember I talked about interception storage, depression storage, through fall, stem flow, everything that's gone, or even lateral flow, deep discharge. Take out all those losses, and then the amount of water that's available for just to flow on the surface is your net rainfall. That's what is shown here, and it is transformed. You are going to do that this afternoon. So we are transforming this amount of rainfall into a hydrograph, or it's called direct runoff. It happens over, storm produces, I don't know, maybe in 1 hour this amount of rainfall it produces. But this hydrograph can have longer time. There is a lag time for generating this hydrograph, okay, because of all the physiographic settings, because of the other conditions that we have on the ground. Leave alone all that for now. So this is the highest point, right? This is the crest, they call. This is the peak flow. When you are talking about flood, this amount, this magnitude is very, very important for us to know. That is one thing. And then this inflection point that I am talking about here is basically a break point that we have. This is the base flow, right? The line that we draw here as the base flow. When you take that base flow out, this is basically the amount of water that is generated by this storm. Assume this is one single storm of 2 inches of rainfall. or 50 millimeters of rainfall. We are transforming that into a hydrograph through a computer model, okay, and that computer model produces hydrograph, and you saw hydrographs even before. Dr. Venkat Reddy sir actually showed you how you saw multiple year of simulation. I mean, when model produces hydrograph, right, we are taking only 1 year. This is one storm hydrograph. This is actually one storm, one event hydrograph, and you need to really understand all these components. Rising limb means it starts building up, because this is again basic hydrology, right? Watershed is big, the rain drops, it starts flowing. The farthermost point in the watershed to reach the outlet will take long time, right? The water, that droplet of water that falls right close to the outlet will end up quickly, right? So the lag that we have for this peak flow from the onset of runoff probably takes about 3, 4, 5, 10 minutes or whatever, depending on the size of the watershed, but it does not reach because of the time it takes for that watershed farthest most point. What is the terminology that we use for calculating that time? Anybody has some idea? Time of concentration. The time of concentration means the time it takes for the farthest droplet of water to show up at the outlet, right? When that point reaches, all the points within the watershed contributes to that outflow or outlet. That is the other point. So when peak flow happens means what? Every location within the watershed already has contributed to that watershed outlet. Does it make sense? Am I mean, kind of belaboring this point over and over? I'm assuming that it's helpful for you to kind of enhance the understanding, right? So this peak flow point can be different for different places. Forested watershed, this 2 inches of rainfall, is happening here, right? But for urban watershed, what can happen? For urban watershed, what can happen? Can you say? Let's actually draw that, because it might help your understanding. This is a very important point for flood. I have lots of slides to cover today, but I am going slow, but that doesn't matter, right? So our point is to really make it clear. If somebody explains to me, then we can assume that you all know. Anybody wants to volunteer? Natural hydrograph, natural system hydrograph, okay. I'm going to just draw a simple hydrograph here. Can everybody see, including the last row? Okay. So this is a natural system hydrograph, okay. I call it natural or forested or undisturbed, whatever people call in different terms, different ways, or whatever I said, right? Natural, undisturbed, right? So this is the peak flow, okay, QP, let's say QP, Q peak. This is the kind of condition that we are seeing with respect to urban watersheds where you have flooding problems. What happens here? Couple of things happening here, right? This peak flow is higher. Sorry? Yeah, base flow might be lower. Also, I'm just, it's a simple graph that I'm drawing here, but to highlight the point, you see the volume of water that we are getting here instantly between this hydrograph is really high in a very short time. Let's say this is 2 hours from here, okay, and if this is, I'm roughly saying 1.5 hours. So we hit the peak flow in a relatively short time, and with the heavy rainfall events, and with all these no loss conditions. Basically what we are talking about, net rainfall here is effectively transformed into storm hydrograph. Net rainfall, right, is small here. That is why your volume or peak flow is smaller. Why? Because you have forest, you have canopy, you have interception loss, all kinds of things. When you pave the roads, when you build the infrastructure, you develop the area, the peak flow happens quickly and more. This is the fundamental reason for floods, right? You should be able to understand now why we are talking about floods in urban areas. It's not just the the extreme rainfall alone. Now we are talking about the characteristics of the watershed that can also create problems, right? You are all with me on this? I'm assuming you are all familiar with this concept, right? From before? Yeah? Okay. So, another interesting quiz that I wanted to ask. It's a dated graph. Don't worry about this graph. I want to show you, now you saw multi-year simulation from the model. It might be a simple exercise for you to interact with me right now. Tell me, I'm going to ask you, some volunteers, anybody, to tell me what you see from this graph. There are many things. I give you a clue. This is how you will also do your own analysis when you write the paper. When you are doing the simulation, let's say by the end of this class, you go home, you are an expert in running the model, then comes next what? You need to be writing your results, you need to summarizing your results, right? Right? So, you have these plots. How will you explain this? Yeah. Say one thing, one person, one point. Okay. So, you are saying, if I interpret Jash Prajapati's point, where you are telling there is a variability that exists from year to year. What about you? Okay. So, these are kind of inferences. Yeah, I agree, the peak is increasing. Yeah, that is true. When you draw that trend line, you can say that for sure, that going up, right? But any other apparent things that you can say from here? Okay, there is base flow that exists, right, or low flows that you are saying. You can quantify that number if you look at the numbers carefully. So, we have got 3 points so far: increasing trend, variability, interannual variability that we have, and there is also low flows, and that low flow is probably more or less low in many years. What other points that you can say? Okay. So, if you start listing them, what more? I mean, 3 or 4 points you have said. Is that all you can say about this graph? Okay. Again, you are extrapolating from this graph. All I am asking is to, when you are writing the paper, this is an important skill you need to have. Let me start. That is Josh's point, first point, which is year to year variation, right? That is apparent from here. What is the annual average discharge? I think, I don't know your name, last one you said the increasing trend. Reshma, thank you. So, Reshma said, increasing trend. Of course, you need to have a mean, condition calculated first to calculate that increasing trend. I infer that based on that. So, you can say, okay, 20 or 50 year simulation that you have, just average it, you get an average number that you need to report to the people that you are communicating. Lowest flow that we talked about, mean flow for the low flow conditions that we can come up with. The highest flow also somebody said. So, here we are talking about the number, right, this amount, this magnitude of 12,000 or something, that what we are talking about. So, we have pulled up so far 4 points. Is that all you have from here? Anything else? What are the wet years? Like high flow years, 1, 2, 3, right? We can say that, pulling up that information. What are the dry years? 1, 2, 3, these years are, you can easily pull them up from the graph, right? And then what can you summarize? 8 of 9 years when stream flow is less than 1 standard deviation below mean occur prior to 1967. So they are kind of doing some additional statistical calculations to come up with something to say about these numbers. What more they can say? 8 of 9 years when stream flow is greater than 1 standard deviation above mean after 1967. So, and again, I don't think it stops there. There is another one. 82 year of stream flow time series indicates an increasing trend. That was also brought out by Reshma. See here, one graph, we are talking about at least 9 points. Why am I talking about it so much? This is the way you are going to really see every graph that you see when you are plotting them. You have to interpret, first of all, for yourself what you are seeing. You know, there is always rush to really run the model, get the results, write the paper, submit. Then it will come back with a rejection. And then you submit again, come back again, submit again, come back again. No, you do a good job first time, get it accepted. How do you do that? By doing a good job of interpreting the results correctly for the reviewer. First audience is a reviewer, and then talking about the scientific community at larger, broader, scope. So that is the kind of example. I talked about single hydrograph before, talking about multiple components. I'm talking about time series hydrograph here to give you a breakdown of how you would interpret your results. Just to give you an idea of how you all can do a good job of interpreting the results that you get from any of the analysis. It could be observed data, it could be model data, but take effort, take pains, take extraordinary effort to really interpret what you are seeing. Don't leave the readers to interpret all these numbers. Hey, I worked hard, I run the model, I produce this graph, it's your job now to interpret yourself. Don't do that. It will not be appealing, it will not be impressive, right? So your job is to explain, even though it may be 1 plus 1 is equal to 2, but still say that it is 1 plus 1, that's 2, right? Like that. And again, same thing, I am talking about another hydrograph, so with multiple points. So all you are saying here is to extract information from the hydrograph. So now I am shifting gears a bit, talking briefly three indices that are really important for flood analysis in the context of India. But I'm shifting gears in the sense, what I mean by that is, we talked so far about storm hydrograph, event hydrograph, the simulation that you are going to do for one single event this year or this afternoon is also an event scale meteorology event, right? Hydrometeorology event. Now we are delving into hydroclimate area, where they are also important. One thing you need to understand is, always we have a challenge. I think yesterday I think Reshma, I think you brought this up in the coffee break. We are collecting the data, right, in some place, and we are trying to interpret the data for another place, or applying that data to make some decisions in another place. So this disparity exists in hydrology in our field. That is a problem, right? We are always, for example, what I mean by that is meteorological data, right? You set up a tower, you collect the data, rainfall, precipitation, or humidity, wind speed, temperature, everything. Where do you normally go and collect? At the lower elevation. I'm sorry, wherever you can put up the station, that is mostly lower elevation. And hydrological data at higher elevations. Basically, you go and do some measurements of biomass or other variables that are of importance that you do in another place. You try to combine them together to draw a picture for the watershed, which is not ideal. General circulation models, now I am shifting another level here. These large scale models are considering this general circulation of the atmosphere, and these large circulations happen because of internal dynamics within the Earth's atmospheric systems, but also there are external forces, atmosphere, ocean, land. We talked about this land atmospheric interaction yesterday. That is also linked with sea surface temperature. What happens in Bay of Bengal, what happens in the Indian Ocean or Pacific Ocean makes the difference in understanding, because they can influence temperature and precipitation for a given region. Apart from all these small scale storm events that crosses, this is an example that I want to say. It's not my graph, right? It's from a source I thought I mentioned here somewhere, but I will add it later. The main thing is this. It's a very impressive graph that I wanted to show you. Some of you might be knowing this. This is summer season, this is winter season. I am talking about this. Pay attention to this jet stream, okay? This is a jet stream we call easterly flowing jet stream. These winds that are pushing, this is Western Ghat, we are somewhere here, right? And winds crossing a warm moist sea, right? What happens? When does it happen actually? What is the consequence of this? What is the consequence of this kind of setup? I don't know, maybe my question is not clear to you. Monsoon. I am looking for that word, monsoon, right? The jet stream. What do I mean by jet stream? There is a warm kind of a pipe flow of air that flows in the upper atmosphere from anywhere from 10, 20 miles to 50 miles. Upper atmosphere, there is always this jet stream moving around the world. That is the circulation. When I am talking about general circulation models came about only based on this general circulation they are talking about. Now you can say, why do they call it general circulation models? Because they want to capture how these motions are happening, because only when you understand that you can relate that to the ground local scale. So this is summer, this is winter. What happens? This jet stream does not move forward, it gets pushed. Cold air from the north comes, and this is the blue line is the cold air. So that is why our temperature is relatively mild when this jet stream goes all the way south and the cold stream comes to the south or northern part of the country. That is the winter situation. We have to consider these when we are talking about three indices for India. One is called Madden-Julian oscillation. This graph may not be clear here. I am going to skip 1 second. Maybe here it's clear. What we are seeing here, this is India, somewhere here you can see, right? There is a kind of anomalous or some kind of a planetary scale circulation in the tropics happens. This is Indian Ocean, right? This is Africa, this is Southeast Asia, Indonesia, Malaysia region here. So this warm water or the atmospheric event or condition is called Madden-Julian oscillation. This happens once in 30-60 days time period, and it drives. Now you have to relate this to the previous jet stream circulations that I am talking about. Depending on this Madden-Julian oscillation, the jet stream can also move back and forth in the subcontinent of India. So that changes your rainfall patterns. When you are talking about rainfall extremes, it is not just climate change, it is not just convective precipitation. They are also driven by this climate index. And especially for India, when this condition exists on the western side, you get more rainfall. When this orange area moves to the eastern part of this Indian Ocean, you have less precipitation or no effect from these MJOs. So MJO is an important part for us to consider. When you are talking about rainfall coming from this ocean, you need to really understand. The other one is El Nino, La Nina and southern oscillation. Basically that is called ENSO. It happens once in 2 to 3 to 5 year time period. These are all natural climate variability that happens because of all the mass, energy and momentum rotation around the world that we talked about yesterday, right? So this is particularly an interesting thing that you need to observe. 1 second, I am going to show you here. This graphic is better than the other one. you see here, just pay attention. I'm going to be done with next 5 minutes on these topics. Okay, we will conclude and then we can take a break quickly. The main thing is, this is warm water, sea surface temperature, right? This is warm water, sea surface temperature. America is here. This is South America. In this, Peru is here. Around December 25th, this particular warm signal that you see is called El Nino. So many of you must have heard the term El Nino, right? The opposite case is cold water. Sea surface temperature is relatively below the normal conditions, that is cold water. And these two triggers different conditions around the world. They say El Nino happens in this year, means every climatologist, hydrologist, meteorologist really pay attention to that. Okay, what's going to happen along with the general day-to-day weather conditions that we are seeing. So these are underlying factors, right? And then on top of this, your regular, day-to-day, weather event that can be combined. When it happens, your flood potential is quantified. So in the interest of time, I'm going to skip all this. The basics I mentioned to you, so you can read when these slides are available to you. This condition is very important to really include in our analysis. I will come to this part directly, which is telling about implications of this El Nino for India. El Nino is an unusual warming of the ocean water on the eastern part of tropical Pacific Ocean near Peru. Warming of this ocean water causes unusually high rainfall, including India. So you'll have to make a point here. Monsoon, people say, oh, we got 400 millimeters of rainfall in 24 hours. Chennai got that, right? So they have to really see, is that on top of the other factors like El Nino, because they modify the jet streams that we get, the monsoonal flow that we get, or how your circulation from the ocean ending up on the land mass. So 2 to 7 years time this repeats, so people have to accommodate that in their calculations. Okay, that is El Nino. The last index is Indian Ocean Dipole, they call IOD. There are 3 conditions. One is called neutral. Basically, the circulation happens without any effect, right? The seasonality exists in all the places, whether it's Africa or Southeast Asia, it happens. India does not have any effect. But look at this positive phase. When positive phase means near African coast, warm water exists that produces more water vapor options. And then you see here convective storms that are really getting developed and that moves forward. So you have year to year monsoon flow, right, of Arabian Sea warming up and bringing moisture. On top of that, when IOD is in the positive phase, it's going to add to that existing seasonal monsoonal flow. So that's going to increase the intensity of rainfall, so regardless of climate change. But of course, people relate to sea surface temperature increase. We saw that in one of the 10 metrics on the climate change part, sea surface temperature is gradually increasing, right? So they can actually modify IOD development mostly on the positive phase side that can impact India with heavy rainfall events. So I will end this 3 index, you can read them. I have the material for you to refer to, but kind of highlights I mentioned. So these indices are available publicly. The links are from NOAA sites. If you go, you can download time series data. They divide the region with some numbers, and then you can extract how PDO changes or MJO changes in our area. Is there a correlation between MJO to flood events that you had in Maharashtra, for example, or is there a correlation between Indian Ocean Dipole, right, to high amounts of rainfall in Kerala? Those kinds of things, those are really interesting questions. So one last point here, there is a debate that's going on in North America about polar vortex, Arctic polar vortex. This is the ideal situation. It's about 20 to 30, 40 miles above the surface. Cold air mass, blue, they are confined here, right? So that's why winter is winter, summer is summer here. This is US, okay? But now increasingly people are saying this Arctic polar vortex is getting broken because of that this jet stream is also modifying its pattern. So the warm air from the south, from Mexico, is entering all the way to Canada, and cold air from Canada is all the way coming to California. So you can clearly see the pattern. This is ideal, this is what actually we normally have seen in the past, but now for the last few years, because of climate change, this vortex is kind of split. So they are allowing this jet stream to have more fluctuations, and they bring warm air, they bring moisture, they change the whole conditions. So underlying conditions like regular year to year precipitation patterns are one thing, but how these large scale circulations can impact precipitation is another thing. So you need to keep that in mind. So I am just creating awareness here. With that I will stop. Do you have any questions before we break for 5 minutes and start with drought discussions? This, of course, I have another one, but we can also talk about that later. Machine learning based flood forecasting that we did. I have a case study. I can provide you the paper, you can read and discuss also, or we can push that aside because today is my drought day. We need to start drought discussions, but somehow I thought I have to introduce these topics to you. So I hope you find it useful. Some of the basics I went through the plants to all the way to global scale discussions, but I hope it's useful. But tell me, do you have any questions, burning questions that you cannot control? You cannot hold off. Any questions? Boring? Yeah, probable maximum precipitation. It needs to be revised, certainly, because of all the changes we are seeing. But historically, I mean, we are using the number developed by WMO for a long time. It is changing significantly. PMP, precipitation or probable maximum precipitation, is one thing, and probable maximum flood they call PMF also. That is also changing. So that is not revised. So WMO is probably going to revise or has done it, I don't know, but recent updates I have no idea. But it is time for revising all those numbers, no question. It depends again on the geography, the location. Yeah, there are models to do that. HMR, Hydrometeorological Report 52. That's again US Army Corps of Engineers. They developed this model. So they transform PMP into PMF. Yeah. 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 Uh, I would say observed data. Gaps. Right. That is a problem. Yeah, yeah, yeah. That is the problem with estimating those numbers. Why we are not able to get the actual PMP is because there is a lack of continuity with respect to the data. There are gaps. Some stations are retired, some stations don't work, some stations are stolen by people. Many things happen, right, with the rain gauges. It's not easy to collect data from the field. So they try to approximate certain things, but PMPs are reasonably established in many places where you have good data, no question about that. But we can continue offline this discussion later, but we'll take a break if you don't have any other burning questions for now. But you know, we have to be here until 12:45, right? So come back here by 12:15, okay? And then we will start with drought. But again, I think when time permits, quickly in 10-15 minutes I can show you the case study of machine learning based flood forecasting that we did for Mahanadi Basin. That paper is available. Anybody who wants to read, I can provide that. But I will also walk you through that what we did. Probably most of you discussed already some of those combination models like GRU, CNN, and then combination of those LSTMs. So we kind of did combination of approaches and came up with a good predictive model for up to 3-day forecast of peak flows that we can calculate. So that's an interesting exercise. I don't want to do that now, show and take away our, we have talked enough on the floods. because combined forces of myself and Dr. Venkat Reddy, you have got, I hope, a decent exposure on this topic, but there is plenty to even discuss more, but we are just quickly, based on the time that's available, we are doing that. Okay, we'll stop here for now. Please come back at 12:15. Upon this, that there is something interesting. I mean, I may have kind of gone from one end to the other end in terms of introducing the basic aspects of hydrograph to talking about plants, talking about infiltration to global scale stuff, right? So it's all over the place. But now when it comes to tying all the ends together and coming up with a plan for understanding how do you go forward. I mean, you have to develop an understanding of all these things when you are running the model, but as a next step, if you are thinking about using some physics guided models and AML techniques to predict hydrologic extremes, this paper is a very good one for you to refer to. So please consider reading it after I discuss with you. There is some discussion on this. I will not do it today. Like I said, it's only a very quick 17 slide discussion that I will have on Saturday when we come back from the field trip, but it will at least help you. So I'm going to wait for that moment. Let's actually, as per our plan, we should start talking about drought, because drought is such a vast topic and we need to really, we are again swinging back and forth between one extreme to the other extreme, right? When you have plenty of water, it's a problem as floods. When you have no water, that's also a problem as drought, right? So that is a challenge for us to predict both, extremes, but that's also an opportunity for our, contribution to science in terms of what can we do about it. So drought is one of the natural disasters. So I'll have tons of papers on this. I've been working on the topic for quite some time now. I will not go through all those case studies. It will not be worth your time as well as anybody's time. So what we can do, we will go through all the concepts that we have, kind of generally drawn from those. I will make the papers available to you. You read whenever you have time between now and before the end of this course. After also is fine if you want to communicate with me about those specific papers. But we are presenting now how you can understand the concept about basic, drought. Drought is such a vague term if you think about it. So let's start drilling down to the details. It's a natural disaster, right? It negatively impacts water resources, agriculture and economy, that we know very well. Global surface temperature has increased. These changes have concerns about the impacts of droughts. You saw, I mean, you have to now tie all the connections here, loose ends. We talked about increased temperature, feedback. If you look at the feedback process that we talked about yesterday, whether it's cloud formation to soil moisture evaporation to how it contributes to increased sensible heat flux, how it really creates the drier conditions, you have to kind of bring all those things together when we talk about drought, right? So global climate change is something that you have been exposed already many times. So what is drought? It is basically defined as a below normal precipitation over a specific period. We are supposed to get, let's say, on a monthly basis here, I am thinking 120 millimeters or something like that. If you get, let's say, 50 millimeters in 1 month, and if you are below that month, average month, then you can call that as your drought condition. It's kind of, slow starting process. It's a creeping disaster that we call, because it develops slower and often unrecognized with indirect consequences. When the rain doesn't come, people will say, oh, we should have gotten this rain, but we did not get. So people ignore and probably move on, right? But only when it persists, it comes to your mind saying, wow, we are now not having water, no rainfall for the last 1 month, 2 months, 3 months. So you saw some regions within the within India are more and more exposed. Marathwada region, for example, if you look at, it's one of the driest region because of the rain shadow is one thing, right? On top of all the other aspects associated with it, maybe more radiation, less retention of precipitation that you have, whatnot, all kinds of things. So it's a slow moving disaster. It's a disaster, and it can also spread over time. A period of abnormally dry weather with lack of precipitation um, to cause a serious hydrological imbalance and carries connotations of a moisture deficiency. So that's another way of defining it. It's word, mouthful of words here, but abnormally dry weather is a starting point for drought. You should understand. So when you see, you have to get the rainfall on a specific time, right? If you don't get that on a specific time, it departs from the average conditions and decrease of water availability in a particular period over time. That is what we can say even with respect to vegetation drying up, for instance. Another definition is a condition where the amount of water which has been expected and relied upon for use in any of man's activities cannot be met for some reason. So we have defined how much we need per day in terms of city people, right? City water supplies calculates that and distributes that water. Where do they get that water from? Maybe from surface water sources, tanks and reservoirs, but they also get from groundwater. They pump that water, put that in this tank and then supply that, right? But if they don't have that water that's available to them, they cannot supply to meet the demand. Then that's also considered to be drought, right? So many definitions, but there are problems in defining droughts, there are problems in predicting droughts, and problems in mitigating the impacts of drought. So there are so many levels of complexities here. We will break it down one by one. So it is hard to know when it starts, because in front of your eyes you missed getting normal rainfall for a given monsoon season. You will think, okay, it will come maybe another time, but before you realize that if it doesn't come, it starts setting up. So you have to then backdate your starting point even. Oh, last season we did not get enough rain. Maybe that was the starting point that we did not realize, and the drought start continuing into the second year also. So that beginning and ending point is very difficult to predict. Drought definition can lead to confusion due to the absence of universal definition of drought. It's a broad term. There is no universal agreement on what we call as one single thing. For floods, we have a clear definition. For this particular location, if you have more than the channel capacity, you call it a flood stage, right? For drought, that's very difficult to say, because it has got a lot of other social implications associated with that. Drought impacts are non-structural hazard and spread over large geographical area. So it is widespread. It's like smog in the atmosphere, right? It can really spread over a large area, and the impact is, of course, can be detrimental for everything, both humans and infrastructure. When we talk about drought, there are specific definitions. Meteorological drought, that is one type of drought. When there is lack of precipitation or below normal precipitation for a specific period of time, we call it meteorological drought. It can be from few days to few weeks. It cannot go beyond that. Few days means, when I say, let's say June precipitation, we should have gotten, let's say for Warangal, 150 millimeters. If we don't get it, maybe you can call it as meteorological drought. What is agricultural drought? A period with the scarcity of soil moisture and leading to crop failure. So there are combinations of meteorological and hydrological factors associated with it. So that's called agricultural drought. So when I said for meteorological drought, June month is the time when you miss rainfall, short time period, you ignore it, right? Saying you may get in another month like July or August, you might compensate what you did not get for June. That might be a, kind of a wishful thinking. But what if you don't get rainfall in July? What if you don't get rain again in August? So it extended from June to July to August now, 3 months. So that is the actual growing season. Probably people want to take advantage of monsoonal rain to raise paddy without irrigation, they can use this monsoon rain to cultivate crops, right? They will not be able to do that. That leads to agricultural drought. So that is the crop season calendar that you can call roughly for the period of growth of crops. Hydrological drought, what do we mean by that? We saw the annual hydrograph. Let's say this is an annual hydrograph, right? So in this case you have 4 months of rain in many regions of India because of monsoon. If you don't get that rain, many rivers start drying up, but they don't show right away. They don't show right away. Ganges, leave Ganges, because they also still get snow melt runoff from the Himalayas. But I am talking about the rivers that are fed by the seasonal rainfall like monsoons, okay? Whether it is Krishna, Godavari, Kaveri, Pennar, whatever, all those rivers that we have that depends on this monsoon, whether it is southwest monsoon or northeast monsoon coming to the region. If you don't get it, at the end of the season, your hydrographs or the rivers that you see will have low heights, low peak flows, low volume of runoff that you have. That's hydrograph. That's a hydrological drought. That is hydrological drought. The next one is socio-economic drought. Okay, so I think this is increasingly gaining traction now, because drought means it's not just we are talking about natural systems, whether it is crops or rivers. We are also talking about the people that are needing this water to be shared. They are going to be impacted. Poverty increases, food famine starts, all kinds of socio-economic conditions develop. So there are metrics to quantify that socio-economic droughts. So when water supply and demand is not met, you are going to have implications on many levels. So that is socio-economic drought. Groundwater drought, what happens to your aquifer? When you 1 year, if you don't get rainfall, maybe it will not drop too fast because these aquifers are large in size underground. But if you don't get rainfall for consecutive 2 years, 3 years, then you can clearly see the water table drops, goes below, and that is called groundwater drought. And on top of that, people, when they don't have enough water for agriculture, for drinking, or for other purposes, they start pumping water during drought. So they even aggravate that. It's a positive feedback, right? When you have drought, you are pumping more water, and it creates more drought, because you are probably depleting water more from these aquifer systems during drought. So that happened even recently in many places, including California. They happened to see that. So another important thing that you need to understand, it's based on this run theory that people have derived some terminology. Whenever you read drought literature, they talk about couple of variables. So I am going to talk about those things here: severity, intensity, and duration. And there is also, of course, the other part that I wanted to mention, the areal extent of the drought is very important for us to consider. So the initiation time is important, termination time is to be known, drought duration and drought severity and intensity. What do they mean by the drought? Let's say this is the average condition, right? Assume this line as an average line. If your rainfall does not happen and then you start seeing the deficit rainfall, that is the starting point for the drought, right? That is the starting point for the drought. And again, if you don't get rainfall enough, it continues for some time, and that is the duration until when you hit back, when you come back to the normal condition of rainfall, let's say, based on rainfall I'm saying here. So this drought part that I'm talking about, right, this drought deficit rainfall that I'm talking about for a certain period, the duration that we have here, right, has got higher severity. Why do I say this is positive side on the left side, up, down is negative? So you can see probably it's going deeper, meaning significant deficit rainfall that we have. In the second case here, if you look at the severity is not there, right? Severity is not there, but the spread of the drought starting point and ending point is there. So, it is called the longest duration drought, that what we are seeing here. And think about the third one here, you have a much intense drought deficit conditions, but for a shorter time it immediately recovered. So, to come out of this situation of such a deep drought, you should have had some hurricanes or cyclones and tropical systems bringing heavy rainfall that saturates the whole area, breaks the drought cycle. So, all this ending point and becoming normal condition here, this point I am talking about, this point, from deficit condition to positive side, same way from deficit to positive, another one, it has to have extraordinary breaking in the system, extraordinary out of normal condition, meaning the drought should be immediately quenched. The thirst of the soil, thirst of the empty reservoirs, thirst of the rivers, they all have to be met with heavy amounts of rainfall. Then you will start coming back to normalcy. So, you have the duration of the rainfall, intensity of rainfall, and then of course starting point and ending point, right, and then the severity aspect of rainfall. And now one thing that is not apparent from here is the areal extent, because drought does not happen in one place. If it happens over a large area. So, then you are talking about the socio-economic aspect of it, right. So, but primarily quantifying all these things is very important, to quantify or to map the drought extent. There are techniques available, that is what we are going to see now in this next few slides. These are characterized by multiple hydrological and meteorological variables, right. I am listing all of them here. I think you know this, we are starting with precipitation always. When you have deficit precipitation and the temperature, when you have more or high, it impacts more evapotranspiration, depletes soil moisture or reduced stream flow, that decreases soil moisture and depleting groundwater. So, these 6 of them that I am showing here has got a direct effect on drought, right. They are related to drought, tightly connected to drought. So, if you take any of these variables and integrate into calculating drought indices, you might be able to quantify the variables that I was talking about before, like initiation, duration, severity, intensity, areal extent, all of those things you can still come up with. That is the main thing that I wanted to emphasize in this slide here. So, this part again I am going to emphasize, like I mentioned in the plant that I showed this morning. Consider this part like a small column of soil that is holding field capacity, wilting point that we already discussed here. This column, the available water is between field capacity and wilting. Field capacity is the highest point, wilting point is the lowest point. If the water goes below this point, plant is dead, right. So, this is the actual available water for plants to extract moisture. So, we want to quantify drought conditions based on available water content or soil moisture condition. Based on soil moisture, that we can come up with what is the drought condition that we have in the watershed, for example. And again, when you have more moisture, you have increased ET, right. When you have less moisture, you have drought conditions, right. When there is low precipitation, you have drought conditions, and soil moisture deficit increases, and then you have to really quantify whether or not intense drought, how intense is that, how severe is that, and all that, right, based on soil moisture. That is one approach. Based on precipitation is another approach, and there are statistical approaches. So, these are some of the indices that I am going to talk about. Standardized precipitation index, this data is already available on a global scale for maybe varied degree of resolution. Basically, I am talking about 2 by 2 degrees they started with, but then in some places they increased to 1 degree, to half a degree, now 10 degree or 0.1 degree, something like that they have come based on the intensity or density of rainfall. SPI is the most popular index because precipitation is measured in many places, right? So it's easy to calculate. They have a mean. I mean, it's not too difficult to extract the condition of the drought based on precipitation. You have average precipitation. Any departure from that average you can categorize as drought. That's what they do in SPI. Okay, in SPI, any departure from the long term average, if it's below, if it's negative, you can say it's a dry year. If it's above, you call that as a wet year. You can do that same thing on a seasonal basis, you can do that on a monthly basis or a weekly basis, because precipitation is measured mostly on a daily time scale. So you can even come up with drought index based on precipitation on a daily time step. Do you follow what I am saying? You can calculate drought based on daily time step very easily. And then this particular entity where I was part of in the beginning, called US Drought Monitor, started in University of Nebraska, Lincoln. They kind of used couple of standard drought index. For example, Palmer Drought Severity Index, SPI, Keach-Byram Drought Index. These are all different types of metrics they used. 7-day average stream flow, precipitation anomalies, and then they came up with, I think I probably have to show you this map first, and that way you can understand. So they came up with a spatial map like this. Before they even put a red dot on the map, what they did was to call the water people in those agencies. Nebraska is somewhere here in the middle of the country, right? Nebraska is here, but they reached out to all the people on a weekly basis and say, hey, did you get enough rainfall this week? Hey, did you get enough rainfall next week? Or whatever they want to compare. Do you have enough storage in your reservoir? Do you have enough crops growing? Do they need enough, do they have enough water for irrigation? All kinds of questions, survey questions they have. On a weekly basis, they really sent out those questions to people to fill out based on what they say, based on the survey, and then based on the real world data of precipitation, stream flow anomalies. They came up with a map. It's a pretty hard work. Basically, every week, Thursday afternoon, they release this map, US Drought Monitor. You can even go and check out this map. For India, I think similar map was started in India also by some other groups in India. IITM, I think, is doing that also, or maybe other institutions like Gandhinagar IIT. But the takeaway here is this: there are categories they define, D0 to D4, abnormally dry, like in these yellow regions, right? When they calculate precipitation and say, oh, they are not coming enough for this week, they call them as abnormally dry conditions. To moderate drought, severe, extreme, exceptional drought is the red dot or dark brown dots here, right? So you can do this for every county. I would say county in US terminology, county is equivalent to our districts here, okay, similar to districts, or maybe smaller than district also, counties. For every county, they have statistics, they have numbers, they have weather data. They were able to pull all these things together and come up with a map. Okay, India has somewhat similar approach also, like using IMD data for every district. But now going back to this USDM, they produce weekly maps, and of course, you cannot get the local scale information from this map. It's only broad approach to this whole exercise of coming up with a map, but it's a lot of work. But then they have automated this process. But then again, questions came up: why are we not using one index versus the other? So, for example, PDSI was Palmer Drought Severity Index, Meteorological Drought Index, based on combination of both meteorological conditions, hydrological conditions, soil water model, balance model is used in this case to come up with PDSI, right. And PDSI calculation is not that simple, it needs all these variables, and even though it is widely adopted, there are some uncertainties associated with PDSI, but it is widely used or developed, and these indices are also PDSI. If you search on a global scale, there are numbers for any region in the world that you can get PDSI, and if you plot just for your watershed how many times that you have above and below the normal conditions, based on that you can start considering what kind of further analysis you can do. I am not saying that you will start there and stop there. It is, any drought analysis, when you want to do, you take the existing calculated metrics like PDSI or SPI, but then you can improve on them based on your local knowledge. Okay. So I will not again go into the details about doing that now, but in the next few slides I will show you. So there are some shortcomings for this also. Many times this PDSI is based on potential evapotranspiration, right. Potential evapotranspiration is another big terminology that I think I need to explain here. When you have plenty of energy from the sun, when the plants are having lots of leaves, we assume that there is no limitation for moisture in the soil, it is energy driven. So it will transpire at the highest rate, and that potential evapotranspiration is not really similar to the actual evapotranspiration. If there is no soil moisture in the ground, if the plants cannot take that moisture for extraction, then your ET is less, right. But they consider potential ET for calculating PDSI, which is not the right metric. That is one example of why PDSI is not reliable. I am giving you an example. But there are other things like assumptions of all precipitation is rain. There are snow regions available, and how do they accommodate when the soil freezes, and then slow response of developing and diminishing drought. So it is very difficult to really quantify the starting point or ending point of the drought based on PDSI. Again, precipitation data is not available. I think you brought this up for PMP calculations, but I am saying that same issue will come for PDSI calculations also here. Again, there is soil moisture condition, reservoir storage data that we need for that is not available. There is another model or index called SWASI, SWSI or SWASI they call, Surface Water Supply Index. Basically, it is the amount of water that should be available for as supply, and if that supply is not available, they call that is a drought condition based on this index. Supply side of water balance equation. Primarily in the US, especially on the western part, they are all snow melt dominated watersheds, meaning you can predict drought based on the winter snowpack that accumulates on these mountains. If you have enough snowpack, the snow season typically starts from late November and it goes all the way up to March, end of March, roughly about 4 months, 4 to 4.5 months, give or take few days here and there depending on the region. So we are talking about December, Jan, Feb, March, 4 months they get lots of snow. All these mountains are packed with snow. So the forecasters, the snow people, go and measure the depth of snow and they say, wow, we got 10 feet of snow this year. This is going to melt to 1 foot of water. I mean, there are conversions based on the density, based on the wetness of the snow conditions. They can convert snow into water equivalent, snow water equivalent. Okay, and then they come back and say by April 1st they release the information saying California has got enough water for this season because they got enough snowpack, because mountains are reservoirs or storage. Even Himalayas, for Ganges, people do that too, because if they get enough snowpack for a given season, they can calculate how much water they will get in Ganga. that is possible, because monsoon rain is one thing. Assuming monsoon brings normal rainfall, on top of excess rainfall, excess snowpack that you have for a given season, you are going to have plenty of water in the Ganges. So likewise, I am saying as an example, but they are all supply side of things. What I mean by that, if you have enough snowpack or if you have enough rainfall, you can then decide that your supply side is met. Supply is normal or above normal, so you will not have drought. If that is the case, if that is not the case, then you will say this year we are headed for drought. April 1st, all the western water managers or western US water managers release this information saying we have enough water, we have not enough water, and all that information, and farmers decide based on that information to put crops in the ground. That is, these people are considered God if they give right information about the forecast, about our the snowpack information at the end of the. So April 1st is a very significant day for them. Yeah, glacier melt is happening. Yes, I mean melts significant. Yeah, yeah, yeah. Glacier, yeah, it's. Yeah, I think we are losing a lot of glacier mountains, right? Generally speaking, because of climate change, but it is, added to the snowpack that's already there. I mean, these glacier mountains also get fresh snow every year, right? So only if they don't get fresh snow, when the glaciers are exposed to sun, they will contribute to runoff. But in most cases, this glacier snowpack, of course, glaciers are retreating. At the same time, they are also, I don't know if I can, maybe I will show in another time. These mountains, let's say you have this amount of snow covering up to 10,000 feet from the top. So they call that snow line is receding, meaning the mountains are losing that snow and they are going minimum. Kilimanjaro, if you remember, in Tanzania, all the glaciers are gone now. Montana in the US, they lost, I mean, they used to have 100 glaciers. Now they got only a handful of glaciers. They are all gone. So it's like a fixed deposit. Once you start taking money from that, it's kind of gone, right, over time. So that is not totally. I mean, it's important, but it's more than that. The snowpack and the rainfall that we get on a seasonal basis will help this particular index, SWASI. But other index I think are also available to calculate, ETDI for example, or soil moisture deficit index. This is what I use, or I developed one such index. These papers, there are, like I said, 20 of them that's available as soil moisture based, not soil moisture based alone, but soil groundwater storage and all kinds of index. So I will talk about or present those papers to you later, but I am just listing all the index that's available. Soil moisture index is an interesting one that I need to show you how we calculate. Maybe in the next class I will show, but I am just listing. Same way with evapotranspiration, people come up with a deficit. They know how much transpiration should happen for a given plant. If it does not happen, then they call ET deficit, and then based on that they can come up with drought mapping. So groundwater conditions are also used to understand groundwater maps. But again, based, like I said, there are 5 or 6 variables that I talked about: temperature, precipitation. I'll stop in the next 2 minutes. Precipitation, temperature, stream flow, all of those variables that we talked about, right? So they can actually be combined in the statistical framework to come up with multivariable drought index, multivariate drought index. PD, or they call joint probability distribution based drought index, that I will come up with a name for that. We have couple of papers on that also. So what I am trying to say is ET is used to calculate drought, and they use both for climate change conditions. Probably you saw BIST paper that I showed, 2019 paper, where we looked at climate change projections, right? But there are also drought forecasting done. You understand the difference between forecasting and projections, right? So far that we have discussed both. Projection means long term, forecast means for shorter term. So drought forecasting is being done currently for up to 6 to 9 months. For that you need good data. Which one is very, very important for that? Precipitation. We don't have good precipitation data up to 9 months forecast. We don't know what's going to happen 9 months from now for precipitation, but rest of the variables we can easily calculate. But drought forecasting is a very important aspect that we will start from there in the next class. I will start about multivariate drought index, and then copula is another one that we use. Then we will come back to using the model to calculate drought, and I will show you how we have done for different places, how we quantified, how we mapped drought, and how it's useful for making decisions with respect to water management. We will kind of end with that. So by the way, these are the two models that we use for calculating, and again one of the models we will discuss, we discussed in the morning also, but WIC model is widely used, but we are using SWOT model for most of the drought cases, which is very effective. Soil moisture developed from this is useful. I will start from joint probability distribution here in the next class, and then continue. Probably by Saturday afternoon we will have a better understanding of what we mean by drought. So today we talked about basics of drought, definitions of drought, what are the variables, how do they define drought, and what triggers drought, those kinds of things. But we did not get into the technical details yet, but we will continue that on Thursday or Saturday after our field trip. With that I will stop. Do you have any questions for me? I know it's getting late. I know I got only one, and no, I think I started by around 10:50 or so, so I took 2 hours anyway. Good. Questions? No? You are all completely clear with everything that's covered, right? It's all simple anyway, so we'll talk more. Okay? So we'll stop here for lunch. We will convene again at 2:15, I guess. HEC HMS is the model. It is working. Good news. So we have our demonstrator coming up with a good plan for today. Once it's finished, if you have time, we can do the rest, whatever left over from the previous days, but it may not take too much time today. So we can be done in 2 hours, hopefully. Okay? We'll stop here. See you again. Head for lunch.
No problem, but did you install the machine? You are ready to run on your own. Yes, I ran it many times back. You can create a new folder. I have not created move around. Yeah. వచ్చిందా వైఫై హాట్స్పాట్ వచ్చాయి అవుదా వాల్ పేపర్ పెట్టారా లేదు అది వచ్చాను పర్లేదు అది ఉంచొచ్చు స్టార్ట్ చేసి ఏమైందమ్మా రావాలిందా డైరెక్ట్గా చేసాను ఇప్పుడు వరకు హాట్స్పాట్ యూస్ మొబైల్ హాట్స్పాట్ యూస్ చేస్తున్నాను నెట్ వైఫై రావట్లేదు సార్ ఇక్కడ చెప్తాం ప్లాన్ వస్తుంది కానీ వైఫై రావట్లేదు మీకు వైఫై కావాలా ఇందులో నుంచి తీసుకోవచ్చు కానీ అందులోకి నెట్ వచ్చింది అక్కడ హాట్స్పాట్ ఆన్ చేసుకొని కనెక్ట్ చేసుకోవాలి అది బెటర్ వైఫై వస్తుంది చెప్పాను కదా అందులో అవుతుంది పని రికార్డింగ్ అయితే అవుతుంది కదా వీడియో రికార్డింగ్ అవుతుంది లైవ్ స్టార్ట్ అయితే ఓకే
So now we are starting this today's afternoon our tutorial session. So now with us our Mr. Mohammad Rafi. So he is expert in this HMS and across models. So he is going to explain. He is the scholar in water resource engineering. So he is extensively worked in this particular HMS and across models. And he along with our other tech students they are going to explain in the next 1 hour, and then we will allow to work with the data set. Thank you. I am handing over to Rafi to proceed further.
So, okay. All of you got it settled? Okay. All of you done with installation, right? Yeah. So we'll start. So I just don't want to directly jump into HMS model. Before that, I'll just introduce you some terminology which are required. So can anyone tell about what is model? So we are doing this modeling, right? So can anyone tell about what is model?
Replicating the real world processes.
Exactly. So this model is nothing but it is a simplified version of a real world system or process or phenomena. A model is similar but simpler than system that represents while approximating most of the important features while doing it. And next one is modeling. So what is mean by modeling? Yes, it is just the process of developing a model is nothing but modeling. And we used to listen one word called simulation. So what is mean by simulation? Used to call hydrological model. So what it will does? So basically the hydrological models are used to simulate the movement and distribution and the quality of water within the hydrological cycle. So they help us to understand and to predict and manage in the future water resources. And these are different types of hydrological models we have. So based on the representation of physical processes, we have empirical models, conceptual models, and physical based models. Empirical models are nothing but black box models. All these machine learning models are black box models. Okay. And next, conceptual models. We have so many conceptual models. They won't integrate all those with the physically what is happening, but they'll just do with the conceptually. And next example, HBD, GR4J, GR6J, all those are conceptual models. So they didn't require any specific platform to do that, but it can be done in R or MATLAB or some Python and somewhere else. And these physical based models are, it requires a specific platform, and in this what will happen, each and everything like from precipitation to how it is converting to a stream flow. So each and everything will happen in a, like it will take the, it will calculate each and everything in a specific equation for using all the physically what is happening. Then you consider all the LULC, soil, what are the management practices that are doing in that particular basin. So all those are they will consider. And coming to spatial, based on spatial representation, we have lumped models, semi-distributed models, and distributed models. Lumped model means it will means total basin will be considered as a single unit. Means the parameters are homogeneous. And next, semi-distributed means dividing the total basin into entire watershed into number of basins. So we can assign different parameters for each basin. So that is called distributed and semi-distributed. Distributed means fully we can distribute it in a grid level. So in a grid level we can assign the parameters. So if you do that type of modeling, that is distributed model. And based on the representation, we have continuous model and event models. Continuous model is nothing but you can run for a long period. For example, 30 years of period. So you can run it though so that it is continuous model. Event model means for a particular flood event, if you run the model, then it is the event based model. For example, SWAT is a continuous model. It is not an event based model. So if you want like SWAT, it can't run for a single event. It will run for the long term period, for 30 years or 20 years or 10 years. But in HMS, it can run for both long term period and also you can run for the specific event, specific flood event. So coming to HMS, so HMS hydrological modeling system. HMS means it is developed by US Army of course through their Hydrologic Engineering Center. That's why the name called Tech HMS. Okay, Hydrologic Engineering Center, Hydrological Modeling System, and it is publicly available domain. It is freely available. There is no amount required to install it and all. It is open source, and it is widely used for the simulating hydrological systems. But we don't get that access source code. For example, if you want to change anything in the model, the process what is happening inside the HMS, that source code is not required. But in case of SWAT, so that in the model it will be modified. But for HMS, we don't have that type of source code, so we have to use it as it is. And this model is designed to simulate surface runoff process of a basin with the precipitation by representing the basin with interconnected hydrologic and hydraulic components. And it can be used in both lumped, semi-distributed and distributed mode for both event and continuous simulation. Mostly it is used for event-based flood modeling design purpose. And this event model means it will simulate the hydrologic process of that particular specific event only. Okay. Continuous model means it will simulate the hydrologic process over a long period of considering all the climate variation, land use variation, all those variations. Yeah. This is HMS interface. So if you open HMS, these are the four things you will get. This is first one is desktop. So it is like our ArcGIS or QGIS map. Okay. And second one is watershed explorer. Here, whatever you want to add, whatever you added in the HMS model, all those will be there in the watershed explorer. And next is component editor. In this, whatever the, for example, any parameter which are related to any specific method, all those parameters are coming in the component editor. This message log, it will just show you the run successful, all those messages. Okay. These are the. This is like I'm jumping into HMS. All these. This is the basic thing which is running inside the HMS. So these are the 4 project files which are required to run the HMS model. So first one is project file. It is simple. It is just creating the new project, and that is just creating the new project. So everything whatever will happen, it will happen in that project file. And next one is basin file. It contains watershed properties, stream network connectivity, and methods what we use for different purposes. And next one is meteorological file. So in this meteorological file containing information about the meteorological inputs like precipitation data, and this control specification file which is important. So here this control specification having information about to what period you are expecting to run the model. So all those detailed information will be stored in the control specification files. So these are the 4 files which are required to run the HMS model. So first step in the HMS model is delineating the model. Okay, delineating stream network and subbasins. Second one is selecting methods for converting rainfall to runoff. Okay, well, I will tell you what is happening from rainfall to runoff and what methods are involved in this. I will tell you. And third one is assigning the parameter for each and every method that we choose for transferring rainfall to runoff. Okay. And basically what will happen in HMS, after delineating you will get the layer like this. Okay, subbasin with all those blue that is stream network reaches. So but this HMS what it will consider is it won't take that subbasins and reaches and all. It will convert this into this schematic network, and it will just show from which subbasin is linked and how this reach formed. For example, see the top one, subbasin 1 and the subbasin 5. Those two are formed and they are linked to subbasin 2. And when the two subbasins are formed, one reach will be coming. That I will explain you later. So basically, what I mean to say is, it won't take this polygon shape and all. It won't worry about it. It will just based on this, it will create this schematic network. So based on this connectivity only, it will work. Okay. from which subbasin to water, which subbasin coming, and where the reach is there, where the junction is there. So it all depends on the stream network. And next important thing is, in this HMS we have so many elements. The first symbol is showing the subbasin element. Okay. So what it will does, what will happen in the subbasin? It will will give model to the runoff rainfall. So it will convert to the runoff hydrograph. And what reach will does, from subbasin to another subbasin, reach will take the water. Okay, from one subbasin, upstream subbasin to downstream subbasin, through reach water will go. And if you have any reservoir in your basin, you can also include that. That is the reservoir symbol in the model. And this is the next one is junction symbol in the model. And next one is diversion. If any water is diverting in that particular reach, that also we can mention if you have the data. And this is the source. Suppose any extra water is coming from particular source, that also you can include it. And next one is sink. Sink is nothing but our outlet. So here entire water will come at that particular outlet. And next, see, this is important one. So what is exactly happening in the subbasin element, and how precipitation is converting into runoff. You see, first we will give the precipitation, then model will calculate the precipitation, excess precipitation after meeting all those losses, canopy losses, surface interference losses, and the infiltration losses. After that, you will get excess precipitation. So that excess precipitation will get transformed to direct runoff hydrograph using transform methods, and then the direct runoff hydrograph, if you add base flow to that direct runoff hydrograph, you will get the stream flow at each and every subbasin. So this is what happening in the subbasin element. So after this, from one subbasin, water should move from upstream subbasin to downstream subbasin. So reach will take care of that. So what will happen in the reach? In the reach, direct runoff hydrograph will enter. Okay. If there is any loss or gain happening in the reach, we can give the data. It will take that, and then you will get routed direct runoff hydrograph. If you add base flow to that, you will get total stream flow. So this is what exactly happening in the HMS. And this is one graphical representation. First we will provide rainfall hydrograph, and then it will calculate losses. It will identify the excess rainfall. Okay, then it will, using the transformation, it will identify the direct runoff hydrograph. After direct run, it will route through all the reaches till reach the outlet. Then you will get the stream flow hydrograph. So during this process, there are three important steps. First one is loss method. Second one is transform method. Number method for loss, SCS unit hydrograph method for transform, and constant monthly method for base flow, and Musfinger method for reach. Okay. Yeah. So after assigning these methods to the model, we require parameters, right? For example, we are assigning SCS curve number method to the loss. So to do that, for SCS curve number, we require curve number parameter. So there are in the QGIS or HGIS, you can calculate the curve number. But we have specified those details in your manuals. And next one is lag time. I will tell you how to calculate lag time. So this is transform method formula. How much time it is taking to reach this as one of the criteria to identify the base flow. Long-term average of minimum monthly flow for each. For example, if you have 30 years of data, you will get value to the January.
If we have a reservoir, dam, above it, then we will have very low value, dry value also.
Yes.
Then what?
Actually, it is not exactly method for base flow. It is one of the criteria to choose base flow. If you won't specify, that is also not wrong. That's why we are minimum is, for example, in January you will get a maximum 2 meter cube per second. That's it. If it is July, August, then only some base flow is there. So we are just assigning. If it is April, the minimum value is 0. There is no rainfall. So like that, it will, based on the precipitation only, we are assigning it.
Sir, the base flow is completely zero. If the base flow is completely zero for intermittent rivers,
Yeah. No, that's what. Na, it is not. We don't have actually base flow values. At particular base flow, there is no source for identifying the base flow. This is one of the way. If we will see the long-term trend of 30 years, how that minimum average value is varying. Based on that only, we will assign. If you, for example, if there is no data, you can ignore it, but we are incorporating it because base flow will be there in monsoon that periods. But without base flow also, you can run the model. It's not an issue. And this is how it will. This is you already know how SAS curve number, and this is the lapse time formula to calculate after getting the curve number, and that is L is hydraulic length of the catchment that you will get through HMS model. So if you incorporate all those here curve number and L value, you will get the lag time. I'll tell you the shortcut way how to find out this. And finally, this is the total data which is required for the HMS model. Digital elevation model, land use, land cover, and soil, that is for curve number. Climate data and hydrological data, which is observed discharge data, where we are simulating the mode flow and simulating the flow. And where is that location, that outlet location, we will get through the shapefile. And there are different applications of HMS model. You can just use it for rainfall runoff modeling purpose, or you can use it for flood forecasting and floodplain management, and reservoir and watershed management purpose, and designing any hydraulic structures, or if you want to assess the hydrologic impact assessment, you can. These are different applications. And next one is finding flood events. So there are many methods to identify the flood events. The best method is the CWC people will tell you in that particular river, that particular reach is what is the warming level. So if you get that warming level, that is best, good enough. You can identify that warming level. And for example, if it is 5,000 meter cube per second, then you take your observed data, then identify the events which are greater than 5,000. So all those are become flood events. So there are many methods I just specified, and if you don't have any method, then if you don't have that kind of information, one method is annual maximum method. Okay, in a year, what is the maximum flow? So like that you can identify, and you can consider that as one of the flood event. That is what we are doing now, and this I will tell you later. Okay. With this, we'll start HMS model. Everyone open HMS model. Yeah, I just wanted to mention, if anybody stuck in between, immediately you call us. We'll come and help you. Okay, otherwise we are going, you are lagging, so you won't complete this task. So if you are facing any problem at any step, just call us, we will come and we will tell you. Okay, don't behind us. Okay, you come along with us. Okay. All of you open? And all of you got download the data. Okay, you better keep it in one folder, in a new folder. And also you create one folder outside. Just create an empty folder. I just created practice. It can be any drive. There is no folder issue. You can create in any folder. All of you created? Yeah, open this HMS. The first step is create new project. Okay. For that, go to File, click New, and here you name it any name, but don't give any spaces in between. Okay. I'm just giving some random name. If you want to give description, you can give. You can give HMS anything, but if you won't give also anything, it is fine. It is not mandatory. And here you can choose the location where you want to save this project. You choose that path that you have created now, that folder. Just choose that path and click on select. All of you reach here. Then here the default unit system, if it is US customary, change it to metric. Okay, all our units are in meters, so you go with metrics. So then click on create. Yeah. If I am going fast, you tell me I will slow.
Or they can raise their hand.
Yeah.
Too slow.
If you are getting doubt, immediately call us. All of you reached here? So after this, the next step is I have to give terrain data, nothing but dem data to the model. Okay. For that, go to components. Go to components. Click on terrain data manager. Go to components. Click on terrain data manager. Then click on new. Here it will ask you the name. Just keep it same. Terrain 1. Then click next. It will ask you to choose the path where the dem is stored. Okay. Just click on this folder symbol. Go to the path where you have saved the data. Here in the Netravati data folder, there is folder called dem. Click on this. Choose this TIFF file. And then click on select. All of you reach here? So our dem is in meters, at elevation is in meters in the raster. So here you are choosing vertical units in meters. Then click finish. just click on this plus symbol. You will see this terrain. See, this is our desktop, right? So this is GIS layer. Still, this is not activated. Okay. So to activate this, we need to create Basin Model Manager. Next step, go to Components. Go to Components. Click on Basin Model Manager. Go to Components. Click on Basin Model Manager. Then click New. Here it is asking the name. Just keep it same. Then click on Create. And then close this window. See here in the Watershed Explorer, this basin model was created. Just click on this symbol, plus symbol, just beside the basin model. Under this, the basin 1 is there. You just click on that. Then this layer is getting activated. All of you reach here? But still our DEM is not visible here. So to do that, here one option is there. Choose the terrain data. Here you choose our DEM with the name of terrain 1. So you can choose this, click on terrain 1. Still it is not visible, right? Because it is having some projections. So we need to set the projections to this layer. Okay. So our next step is projecting, means assign the projections. Okay. To assign the projections, click on GIS, the top, click on GIS, click on coordinate system, here you can choose this option predefined. Then under the type you can choose universal UTM. Actually this is Netravati basin, which is west flowing river, starts from Karnataka, it is in the Karnataka. So it is falling in the 43 north. Okay. So here we give 43. Hemisphere, northern hemisphere. The datum, choose WGS 84. All of you reached here? Then just click on select. So now you can see the coordinate systems, UTM zone 43 north, WGS 1984. So you can just click on set. Just click on set. Okay. Then you click on this basin symbol. Then click on this save. Click on save. Otherwise you can click Ctrl S. You can adjust this. Everyone are able to see the dam?
So you can ask a general question about all the flows.
Yeah. I think here that level was not there. So actually this is Western Ghats. The flow is moving from here to here towards west. Okay. We'll get to know once you delineate, that time streams will be generated. That time you will get to know very clearly. Okay. Our next step is we have provided the gem. Our next step is we have to give the precipitation data and then we have to assign the methods which can convert precipitation to runoff. Right? Before that, one simple step, you have to assign the methods for different methods for different processes. So to do that, just go to tools, just click on tools, then go to program settings, go to tools, then click on program settings, then click on default, then click on default. So by default, here you can see the last method was calculating using initial and constant method, but we thought of using SES curve number method, right? Just choose that SES curve number method and then transform using SES unit hydrograph method. Just click this, and for the base flow using constant monthly method, the precipitation was specified hydrograph. That's it. Choose these three methods: SES curve number, SES unit hydrograph, constant monthly method. Yeah, Muskingum. Yeah. Reach routing up. Reach routing, you choose Muskingum method. Then click OK. Muskingum. Yeah. Then just save it. Now we have done with which method can be used to different process. Okay. Our next step is giving precipitation data to the model. Yeah, delineation. Yeah. So next step is delineation. Okay. For that, just go to GIS. I'll explain you this delineation, how it is happening. Yeah, you look into the slide. So you look into the steps, how delineation is happening. First, that dam contain elevation values, each and every grid, right? Our dam was SRTM 30 meters dam. So for each and every 30 meter cell, 30 by 30 cell, you have one elevation value. Okay. Then first step is fill sinks. So if the dam contain any artificial depressions, or it due to caused by any mistakes in the data or resolutions, or this, what it will does is it will fill those sinks, first step, and then it will identify the flow direction, how the flow is moving using Diet algorithm. Okay, the flow will move from in all the directions. Wherever the steepest slope is there, flow will move into that direction. So it will identify the flow direction. Then it will do the flow accumulation. So each and every cell is each and every cell is receiving water from how many cells. Okay, it will accumulate it. Then we will provide the model with some, to identify the stream. We will provide some area, like to identify the stream, how much area should be contributed to that particular cell. We will provide that threshold. So based on that threshold, streams will be generated, and then based on the junctions or any confluences, then it will divide the total watershed into number of subbasins. Are you clear? So this is what we are doing in our model. So first step was go to JS, pre-process sinks. So it will fill the sinks. That is done. Next step was flow direction. That will come. Just click on this pre-process drainage. It will identify the flow direction. Depending upon the system you have, it will take that time. It won't take more than 2 minutes. Welcome. Like this, streams will come. Next step is all of you reach here, pre-process drainage. Then go to JS, click on identify streams. Here we need to specify the area so that much area is contributing to that particular cell. So that will be identified as a stream cell. Just specify some number, specify 50. I'll show you what will happen if you specify different area here. Just specify 50. Then click on OK. You see the stream is identified. Stream came like this. All of you reach here? Now just for the clarity, you just see here first. There are so many layers here. You can remove those layers just by right click on this space, map layers. So all the rasters, whatever the generated here, all will be there here. For example, we don't require any sync raster now. It is already done. Just remove it. Flow direction, flow accumulation. Now you can able to see the main stream. Just click on, just right click on this space. Go to map layers. Then you can just uncheck it so that those layers will not be visible here. All of you reach here? So the next step is where we are interested to simulate. Okay. So this basin was flowing, like water is flowing from here to here. So our outlet should be somewhere here. We have to select the outlet where we have the observation data, where we have CWC stream gauge station. So that will be act as our outlet. So to identify that location, I just created one shapefile. Okay. To add that shapefile here, just click on view. Click on view. Click on map layer. You can go here, right click and you can go like that also. Then click on add. Click on add. Here choose the path where your data is there. Here one folder is there, Netravati outlet. Just open that. Select that .shp file. Then click on select. Then close this window. So here you can see the outlet shapefile came, outlet point where we have CWC observed stream flow data. Zoom to that point. Okay, just zoom this to that point. Zoom it like this. So now we need to select outlet point. This is the we just added this shapefile to identify where the at what location we have the outlet point. So it will be in the reach stream. So this is the point. You just select this breakpoint creation tool. Okay, just click on this breakpoint tool and just parallel to this, select the point on stream, in the middle of the stream. Don't do it outside the stream. It should be within the stream. So it is fine, you just do it in the stream. Somewhere parallel. Yeah, somewhere parallel to that point. Okay, created. Then just we can give any name. I'm keeping as it is breakpoint 1, or you can keep outlet, or you can keep simulated station. Battery.
There are spare batteries I saw.
one important observation here. So these subbasins are based around the threshold what we have mentioned at area threshold. We have mentioned at here 50, right? So with that 50 means that particular cell is contributing water from 50 kilometers per area. So based on that, these many subbasins are coming. Okay. Now you see, if I change the, I'm just changing the threshold to 500. I'm just changing the threshold to 500. Again, click on delineate elements. Just click on delineate. Now we have increased the area, right? The subbasins will get decreased. See now, I think only five subbasins got formed. Okay. See how many subbasins should be created. It is depends on your what you are looking for. For example, if these many subbasins are there, means when you are assigning the parameter values, you need to assign all the parameters for each and every subbasin. Okay? But see, that means what? We are providing parameters for each and every subbasin, means we are considering the spatial variability of all the parameters. So here some rainfall will happen, here some rainfall will happen, or there some land use is there, here some land use is there. So based on that, our curve number will be different from subbasin 1 to subbasin 2 and subbasin 2 to subbasin 3. So if your work is towards focusing on accurate representation of stream flow, then you have as much as possible you create that many subbasins. Yeah. So that nothing, simply like each and every process in the HHMS will happen for each and every subbasin. It will calculate stream flow for each and every subbasin, and then it will route through all the subbasin till the outlet. So if your area is small, then you are considering the spatial variability more concisely, like more clearly, like that. If the spatial variability you are considering, of course the whatever the output you are coming, that will be more accurate, right? It is same. So it depends upon your problem what you are solving. So if you are focusing on the more accuracy, then you have to delineate as many as possible. But on the other side, it will also increase the complexity of the system. If you are having good enough system, then you can go for maximum number of subbasins. So it is, you have to trade off between this thing, the accuracy what you want and the complexity what. So depending upon those two, you have to fix the subbasins. Okay. So as of now, for class, for this demonstration purpose, we are going with the lumped model, means single subbasin. Okay. So for that, see now, even though if I keep 500 as a threshold, I got 5 subbasins, right? So to get into a lumped model, what I need to do? We need to increase the threshold or decrease the threshold? So again, we need to increase the threshold. For that, go to GIS, identify streams, just keep it 2000, keep it 2000, keep it 2000, click OK, and then again go to GIS, click on delineate elements. If you want to give these prefixes, you can give, otherwise it's fine. Click on delineate, click continue. Yes. Yes, sir. Yeah.
So if I just add some points here between this model to SWOT model, you can delineate the boundaries just like this, exactly like this, but with one subtle difference. Here, what are we using to delineate the basin? We are using DEMs, right? Basin is primarily divided based on the DEM. In the SWOT model, it is little more advanced by the way of defining three different inputs. One is soil, the other one is slope. Slope is based on DEM, and the third one is land use. You will choose all those three layers, and then you give the same thing, like the threshold they call HRU. You remember this morning Dr. Venkat Reddy mentioned hydrologic response units. So where you will mention, the smaller the number, of course, you will have more number of HRUs. And if you mention a bigger HRU number, then you will have lesser subbasins or lesser HRUs overall in the basin. So this is kind of a one step lower or primitive model when it comes to delineating the basin. We are just using the DEM. But if you want to really go sophisticated in the SWOT model also, you can do the same exercise by using all these three layers, and we can have a better definition. See, for example, in the first number he was using, 30 or 50 when he used, these mountainous areas were actually in a separate subbasin. But then in the second example, this and there was some plain area was also included. But now everything is lumped into one, right? So if you are using three different layers or three different inputs of soils, land use, and slope, then you will even better define the spatial variability. For hydrologists, like Rafi was talking about, you need to show the spatial variability or heterogeneity with respect to many things, not just the DEM, but vegetation and soil. They are also controlling how the runoff is going to be generated in the basin. So, but this is just a simple example, but you can build complexity with advanced models like SWOT.
Anyway, that we will show you on the Monday. Monday afternoon. Monday afternoon, we are planning to demonstrate that model. It's not working. So now, one lumped model is created, right? So if you are focusing on semi-distributed model, so depending upon your complexity and your problem accuracy, then you can go choose a number of subbasins. Okay? And I forgot to show you, I will just see here, because suppose for example 10 subbasins are there. Out of 10 subbasins you identify that 2 subbasins are having homogeneous properties, so you can merge those 2 subbasins. I'll just show you that step. So these subbasins are there, right? For example, subbasin 3 and subbasin 2. You know that those two are homogeneous. Then you can just select just control. You can just select like this. So just control and select those two. And then go to GIS. There is option called merge elements. But before that, you need to choose like these two should be like adjacent to each other. This is the condition when you are merging. These two should be adjacent to each other, and those two are referring to one range. Then only you can able to merge. Okay. So if you just click on merge, these two subbasins will become one subbasin. So the complexity will reduce. I'm just again going to the lumped model. All of you reach here. So now one lumped model is there, right? So what we need to do? We need to assign. So we have chosen 3 different methods, right? for loss, transform and routing. So now we need to assign those parameters to the models, to the model. So for that, just click on this basin. There is a plus symbol is there. Just click on this and then click on sub-basin under this basin 1. Under the basin model, basin 1, under the basin, sub-basin 1. Then here you can see in the component editor, it is already, so we have changed in the default settings of the model itself. So automatically here you got SCS curve number method for loss, SCS unit data graph method for transform, constant monthly method for base flow. If you won't choose there, you can also choose from here. You can also choose here. Okay. Then you need to, for example, for SCS curve number, what is the parameter? Curve number, right? So we have to assign the parameter here, parameter value. Just click on loss. First method is loss. So we have curve number. Actually, there is a procedure to calculate curve number using your land use and soil. That you can that we already mentioned in the user manual. You can also do that, but without doing that exactly finding the curve number. This is one of the shortcut way. You just give some random number here. And just usually this curve number will vary generally for all the bases. It will vary from 60 to 85 or close to 90. That's it. So somewhere in between this you fix one value, because finding this curve number it will take again one more hour. So that's why we kept all those steps in the user manual. Here I am keeping 70. Just assign 70. This is for last method, curve number value. And next, in the transform, we have lag time. We need to specify the lag time. So this is also you can calculate through that formula. Okay, for each and for example, if you have 20 subbasins, then it will take more time to calculate. For each and every subbasin, you need to calculate curve number and lag time. So it is a time taking process. So we can assign some usual between values. There are ranges for this. Anyway, next process we are doing calibration. So that time these are all the parameters are automatically adjusted. I'll tell you that time. You just assign some 1500 minutes. 1500 minutes lag time. And next one is base flow. As I said, we don't have base flow observation data. We are taking long-term monthly average. Okay, I'm just giving some random values here which are meaningful. Just give some 5, 6. That's it.
Sorry, there are more subways. It will be very difficult to
Yeah, I'll show you that. If there are more subbasins, it is very difficult to keep for each and every subbasin this flow, right? I'll tell you, I'll show you that how to keep. So when in the real time, when you want to identify the base flow values for your subbasin, you can take the flow, long-term flow, 30 years flow, then you identify the long-term minimum monthly average value, and those values you assign here. Okay? So now all these for one subbasin, right? But what if we have multiple subbasins? But if you go here in the parameters, same, there is in the parameters there is option called loss. Just see here, you don't follow, just see here. The loss, SCS curve number method is there. Here you can enter the value. So for example, 20 subbasins are there. From Excel, you can copy those 20 values, you can paste it here. Okay? Same way, for example, for the transform, 20 subbasins will come. Just copy paste those 20 values. Okay? This is another way to enter the values. Just click on save. So with this, in the subbasin element, whatever the process is happening, all those methods we have mentioned, those parameters also we have mentioned. And here one thing is missing. If you see, there is only one subbasin, so there is no reach. There is no reach. If you have multiple subbasins, then reach will form. Reach will form only when two subbasins are joining. So what reach will does, will take water from subbasin outlet from upstream subbasin to next downstream subbasin. So during that process, routing will happen. But in the lumped model, we have only one subbasin, so there is no reach. But when you are doing for semi-distributed model, same way you have to choose Muskingum K value, Muskingum X, Muskingum K and X are the parameters. I'll just next, after this lumped model, we'll see the semi-distributed model also. I'm just telling like how to proceed. Okay? If it is a semi-distributed model, then you have to assign the parameter values for Muskingum also. Okay? So with this, all the things are done, but we are missing with one major. What is the source? Rainfall. So our next step is giving precipitation to the model. Okay? So for that, we need to create one time series manager. So for that, go to components. Go to components. There is option called time series data manager. There is option called time series data manager. Just click on new. Forgot. Data type. Data type is precipitation gauge. Okay, keep it precipitation gauge. There are multiple options. Discharge gauge, stage gauge, all those are there. Just keep it precipitation gauge. Click on new. So keep it named as it is, gauge 1. Then click on create. Click on create and then close this window. All of you reach here? So next step, see in this Watershed Explorer, you can see this time series data. So just click on this plus symbol. Click on this plus symbol just beside the time series data. And then click on this precipitation gauge, this plus symbol beside this. Click on gauge 1 and plus symbol also. So keep cursor on page 1. So we have precipitation, daily precipitation data. So see, you understand here, whatever we have chosen here, the corresponding parameters or corresponding information which is coming in the component editor, right? So you just click on cursor, gauge 1 and then see time interval, keep it on 1 day. Keep it on 1 day. This is the advantage of HMS model. You can run for the 15 minutes, 20, 30 minutes, but it is not there in the SWAT model. So you can run this for, like, if you have observation data, precipitation or observed stream flow data, for 15 minutes also you can do this. Okay. So choose here 1 day, then come here, you just click on these dates, yeah, before entering here, open the folder where this data is there, Netravati data, just open this rainfall discharge folder, open that Excel file, yeah, rainfall discharge. I think we have given 2007. Open this Excel. Just open it. Just check. Open it. Open that Excel file. Two sheets are there. Just go to rainfall sheet. You just check here what is the last date, 2008 or 2007? 7 only?
7.
Okay, fine. So we have precipitation, daily precipitation data from 2005 to 2007. Just enter the date. 1st January 2005. This is the fixed format. 01 JAN, 3 letters, then 2005. Then start time 00. Same end date 31st December. Seven, right? Yeah. Plus year wise is there. Okay, fine. Okay, just enter those values. January 2005, 1st January 2005 to 31st December 2007. So next thing is table. Just click on table. Here we need to copy paste the data. Okay, but in your Excels, I think there is separate sheet for 2005, 2006, and 2007, right? Just make it into one sheet. In a single way, I just show you. Actually, we didn't forgot that to give in the updated one. Just make it like this in a sequence. Date's not important, but you just give correct data, correct precipitation data. Just arrange it in a single column. Arrange it in a single column. 2005, after that 2006, then 2007. Google Sheets. I will try in Google Sheet. Google Sheet. That's what I'm doing. After this, we make the goal systems. So what I'm saying, keep in a one stretch. There are 3 years that I did. Open that 2007 sheet. In that, I think data is there. Full stretch data is there. All of you listen. In your Excel sheet, there is one sheet with the 2007, right? You just in that from 2005 to 2007 data is there. Just copy that. Okay. Okay. Yeah. Copy data from 2005 to 2007 here like this. Just copy the data. In 2007 sheet, it is the full stretch data. From 2005 to 2007 data is there. Just copy that. Yes. So this is the 3 years precipitation data. If you see this precipitation data, it is following the seasonal pattern. Right? In the monsoon, there is a high precipitation. From November onwards, it is reducing. Again, it is starts on at the end of May. Then again, so it is following seasonal pattern. So there could be a chance of flood during the monsoon, either in July or August. Okay, it is always better to see whenever you have the data. It is always plot and see how the data is varying. So you will get to know the significance of it. Otherwise, if you just think it as a number, then you won't feel that. If you just plot it, then you will get to know the significance. So before this, we didn't plot it, so we didn't identify this variation is there. So after plotting, we got to know that this variation is there, seasonal pattern variation. Okay, so copy the data. So come to HMS. Here, keep cursor on the first row. Keep cursor on the first row, and then just click Control V. Control V. Paste it. Copy from Excel, and then paste here. You just cross check is that data is filling or not. You just up to the last point. The data is correctly pasted or not. You just cross check one time. Anyone facing any problem up to here? All of you reach here? Don't take tension for the first row. First row, the data was not visible. That's it. Data will be pasted correctly only. Corrected only. Okay. Then, if you want to see the hydrograph, you can just click on the first save here. Then click on graph. It will also give you the graph. Hydrograph. So after this, save it. So with this we have given rainfall data and we have specified all the methods to convert from precipitation to runoff. So now next step is to run the model. Okay. So before running, one step is there. We need to tell to the model that the precipitation here we assigned is correspond to subbasin 1. Okay. If you have multiple subbasins, for each and every subbasin, in the same way you have to give precipitation data. And one more thing I want to tell you, how I have come up with this precipitation is, IMD will give you 0.25 precipitation data, right? 0.25 by 0.25 degree. So I just identified all the precipitation grades which are falling in the subbasin. Okay, and then took the average of all those grades. Okay, then that average precipitation what I am giving here. The same way, when you are doing for multiple subbasins, you need to take out the subbasin shapefile that I will show you. You need to take out that subbasin shapefile from here, and then you identify in that particular subbasin which grid is falling. If it is 2 or 3 are falling, you have to take average of it. If it is only 1 falling, you have to take that value. Okay? Okay. In this, suppose for example, if you have multiple subbasins. If you have multiple subbasins, then how to export that subbasin shapefile from here? Okay, that I will show you. You just see here. We are not doing that now. For example, go to GIS. Here there is an option called export layers. So here layer type is subbasin. If you click on next, it will ask you the folder where you want to save the subbasin shapefile. Here in our case only one subbasin is there, so it will get exported. Suppose if you have multiple subbasins, that shapefile will get exported. Then in the ArcMap or QGIS, you can identify in each subbasin what precipitation is what precipitation grid is falling. So that corresponding precipitation for that particular subbasin you need to give here. Clear? Okay, that step. Next step is we need to tell the model that this corresponding precipitation was, so this precipitation belongs to the subbasin 1. So for that, go to components, go to meteorological model manager, click on meteorological model manager. In the components, meteorological model manager, just click on new, then it will, this is just name, just keep it as it is, meteorological information. Then you just close this window. Here that meteorological model is created. Just click on this symbol, plus symbol, then click on Met1. Then click on Met1. So there is an option in IKHMS. If there are any missing values in your information in your rainfall data, it will interpolate it, it will calculate it. Okay, if you there is option set to default. So it will automatically calculate it. If you choose about to compute, about compute means it will automatically fill that missing value. If you keep set to default means if any missing value is there in the provided rainfall data, it will throw you error. Okay, but as of now, whatever the data we have given, there is no missing data. Okay, then go to basin. Here we need to choose basin 1. This asking include subbasins. Click on yes. So in the basin model, it will include the subbasins. Just save. Save it. Done. All of you reach here. So next, click on this specified iTograph. Click on this specified iTograph. Here we need to choose for the sub-basin 1 is gauge 1. This gauge 1 is precipitation gauge 1. So if you have multiple sub-basins, then corresponding sub-basin gauge you have to choose here. For example, sub-basin 2. Then if you name it as gauge 2 in the precipitation, you have to choose gauge 2 here. Just click gauge 1. Click on save. All of you reach here.
After basin, adding basin.
This one. Just click on the specified iTograph. Click on. So all of you reach here. So now everything is done. Everything we have given. Now we need to run the model. Okay. So to run the model, yeah. So what period you want to run? To run the model means what period you want to run. For example, we have precipitation data from 2005 to 2007, right? We will run for the full period. Okay, we will run for the full period. So for that, we need to create one control specification manager. Click on this. Just go to components. In the components, option is there, control specification manager. Click on new. Click on new, then create. Close this window. Same steps. Control specification is created here. Just click on here. And then click on control 1. Just click on control 1. Here you have to specify the what time period you want to run. So you run it for 1st January. Type in the same way, that is the fixed format. 01, 3 letters of the month, and then year. And first letter should be capital. 2005. Start time is 00. End time is 31st December. (2007), right? Okay. Then end time is 00. Be careful here. Time interval is 1 day. When you are entering these dates, keep it in the same format, again it will throw error. Okay. This time interval is 1 day. Then, so just save it. With this, we also mentioned the at what period model has to run. So next step is to run the model. For that, click on compute. Click on compute. Then click on create compute. Click on simulation run. Then just name it as run one on self. Yeah, here it will ask, it will link with the what we like, whatever we have done, the watershed explorer, it will link with everyone. So basin 1 means it will take the properties of the basin 1, means not sub basin 1, the basin which we have created. For example, you can do for 2 basins simultaneously. Okay. So this is basin 1, and next metallurgical 1. In that our precipitation is mentioned, it is belongs to which sub-basin. And next control 1. So if you, we can have so many controls, means we can, for example, if you are doing for flood events, we will have so many control specification files. For each and every event we will have one control. So we can choose for the what period you want to run. Just click on finish. All of you reach here? Then just save it. Click on compute. The component editor. Click on compute. Click on compute. Here our simulation run was created. All of you reach here? Just click on this run one. Just this you just forgot, warning is quite normal in HMS. If it is an error, then it's create a problem. Time series match. You will see. If it is while after running, if it is a problem, then it will throw error. Otherwise, it will be not an issue. Just click on run one. Then here there is symbol, run symbol. Just click on this. Select run one. Then click here. If there is no errors, it will run. If somebody did any mistake while entering the data, make an error. Yeah, see, read that error, what is there? December base flow is not mentioned. Just see something, if you are getting error, just see here in the message log, it will be displayed. That error belongs to, like, for what, which step. Read that and you redo it. Yeah, it is done. Dates are wrong. sometimes after entering the dates, without saving it, if you run means again the date issue will come. Okay? Anyone getting any error? Nothing? Yeah? Done? Done? Yeah, to default. That's fine. Actually, you can keep both. That is not the issue. That is the issue. Error solved, na? All error.
That was given over by the our teaching. Okay, I will show how to after it is over to show and I have included it. There is in the tutorial, there is an empty website where you directly upload the shapefile and get the data, but the output is in netset. I have also included a Python program to convert the netset file to CSV pixel. Then you can average it. Yes, ma'am. No, you see? You have to obtain that for verification. We have not used this sheet very.
I'll just 5 minutes. I'll show the results.
Several operator means you just need the values of this function, like in a port. You just need the values of the presentation days mentioned.
Okay? No one is getting error, right? Yes. Done. So now see the results. To see the results, just go to results. Just go to results. Click on this plus symbol, simulation run. And then click on run one. In the results, click on simulation run. Under that, run one. So here you will get output for each and every subbasin. Okay, each and every subbasin, how much stream flow it is generating, then how much it is transferring to the next subbasin. All those information will be computed. So here, just click on sync one. Sync one means outlet. At the end, right? If you click on this graph, yeah, this is how the flow is. Okay? And you can also see the summary table. What is the peak discharge the entire period, and what is the value. Everything you can see here. Yeah. And also same results you can see for each and every subbasin. So the bottom one was hydrograph, the top one, the blue one was excess runoff, the red one was loss. Okay, so like this it will calculate for each and every sub-basin, then it will route through all the sub-basins, then it will give you the total stream flow at the outlet. So this is the results. So now we got the results, right? So how will you check it? Is it correct or not? We need to evaluate it, right? We just took random curve number value, random lag time value, and we run it, right? So with that we got this pressure, this flow, but we need to evaluate it, whether it is matching with the observed or not. Okay? So that we will do after a tea break. Just save it and minimize it. Okay, so what we have done, we have run the model, right? So this is our simulated flow. So next step is to evaluate this, right? So we need to check the performance of our model to compare with observed data. So observed data we have already given. So we need to incorporate that observed stream flow data into the model, okay, to check the performance. So for that, go to components, go to time series data manager, then here data type, choose discharge gauge. We'll go a little bit fast, have less time to complete. Choose discharge gauge, click on new, then keep name gauge 1, create, components, time series data manager, discharge gauge, create, and then close this window. So here in the component editor, choose components. Here you can see the discharge gauge is created, right? Just click on this plus symbol, click on gauge 1 under discharge gauge. Here, same way, how we have entered a precipitation, the same way, choose here, time interval is 1 day precipitation, save it, and then click on this plus symbol beside the gauge 1, click on the dates, yeah, time interval is 1 day, and see the start date is 1st January 2005, 31st December 2007. Save it. One more time. After saving, just check the dates are changing. If that's changing, again you do it on time. Okay. After that, click on table here. Same. In the Excel, there is discharge sheet. In that discharge is there. Just copy that discharge, paste it here. Open that Excel. That Excel discharge sheet is there. Go to that sheet. Go to discharge sheet. So copy from 2005 to 2007. 2006 is there, 7 is also there. 8 is also there. So select up to 2007. Select up to 2007. We are running model from 2005 to 2007. Select discharge data from 2005 to 2007. Just copy that. Copy that. Just click on first row. Just press Ctrl V. Paste it. And then cross check it. Is that completely filled or not? Once it is okay, then save it. Once it is okay, then save it. All of you reach here? So we have incorporated the observed flow into the model, but here we need to give this connection. So this observed flow belongs to that particular outlet, right? So for that, go to sink here under the basin 1. Go to sink. Click on sink. Under basin 1 in the basin model. Click on sink. In the component editor, here you will see options, right? In the component editor, options. Just click on that option. Click on options. Here we need to specify. So what we are doing, to that particular sink, we are assigning this observed flow. Okay. So here observed flow is none. Select gauge 1, which is discharge gauge. Clear? Just save it. Save it. Okay. Then come to compute. In the component editor, come to compute. Click on compute. Again, just select run 1. That's it. Now we need to run. Just click on run 1. Then run it. Just check any error is coming or not. If you are giving correct, then no error will come. Anyone getting error? No, right? Up to this done, right? So now, to visualize these results, is it matching with the simulated data or not? So go to results. Go to results. So in the sink, there is option graph. Select that graph. Now you can see observed flow with simulated flow. So with this graph, what you understood? That black one was observed flow, that blue one was simulated flow. So if you see here, the simulated flow was very low. It's not capturing the peaks, right? So by seeing these graphs, we get to know that whatever the model we have created, it was not able to capture the peaks, but it was following the seasonal patterns, right? So what? There is another way to check the model. This is one way, graphical way. So another way is check the with any statistics, right? You need to check with any statistics. So there is one metric, mass subtle efficiency (NSE). So it will give you the how our simulator is predicting well with respect to observed flow. If it is predicting good means NSE will be close to 1. If it is less than means if it is close to 0 or negative means it is not unable to predict. So it was somewhat 0.683. Okay, so almost it is good actually. So but it is not it is satisfactory, but it is not good. So what is the next step? Huh? That is coefficient of termination. R square. R is different. R will give you the relationship between observed and simulated flow. రాదు సంథింగ్ ఏదో వాల్యూ చిన్న మిస్టేక్ చిన్న వాల్యూలో ఏదైనా చేంజ్ ఉన్నా డెసిమల్స్ లో చేంజ్ ఉన్నా వచ్చింది అలా మిస్ అవుతే రాదు మిస్ అవుతే ఎలా వస్తుంది No, it's fine. Actually, it was space flow somewhere else. If you not exactly given this, then it will solve that problem. It is fine. So our model is satisfactory, but we need to improve the model performance because even though the metric was 0.683 satisfactory, but it was not able to capture the peaks. So if you use this model to predict the floods, you may not able to find it, right? So what we need to do, we need to improve the model performance. I told you now in the first step itself, we have taken curve number, lag time, just randomly we have taken. So we need to optimize those parameters in such a way that this simulated should come close to observed one. That process is nothing but calibration. Okay? Calibration is nothing but adjusting the parameters until we get best match with the observed data. This process is nothing but calibration. But before that, before we are starting going with the calibration, we want to focus on flood events, right? This is continuous mode. We are run from the 2005 to 2007. It is we are not done with the event. So this you can done with SWAT model also. Same steps means that there the procedure is different, but the result will be like the same thing. It will also run for the continuous time period. But the advantage of this HMS model is we can run for the event model. You can that particular event. Okay, that particular flood event. So now we'll see what are the flood events are there in our data, and we'll run for those events, and we'll calibrate and validate for those events, because this HMS is only it is best for simulating the flood events. Okay, so for that I told you, right, there are many methods to find out the flood events. As of now, for this river we don't have that warning level of this flood. So we are identifying through annual maximum. Okay, here we have 3 years data, 2005, 2006 and 2007. So we will identify 3 events. The maximum flow which is occurring in the 2005, the maximum flow which occurred in the 2006, the same way 2007. So we'll take those three events, will perform, first we'll check these parameters are fitting for that event or not. Okay, then if it is not fitting, we'll improve it through calibration. Then we have to test, we have to do validation for another event, for second event. Then if it is good at validation also, then we can predict for the 2007. So this is the idea. Understood? Okay. So any model you take, we have to do these three steps. Means these two steps compulsory: calibration and validation. Prediction, if you are interested, you will do; otherwise, not. Okay. So out of three events, we'll take one event for calibration, one event for validation, one event for prediction. Validation means, for example, after adjusting the parameters in a calibration period, we will take the same parameters and do it for the validation period. If those parameters are still giving good performance in the validation period, then the parameters whatever you have chosen, that was correct. You can use that model for the prediction. For example, after doing in the calibration process, you may get good results, but if you use same parameters in the validation period, you may not get good results. So that means what? The parameters whatever you have taken, they are only suitable for that period, which is not true, right? It has to suit for all the periods. So again you need to do calibration, again you need to do validation, then the both are satisfied, then use those parameters for product in the future. This is the concept. Okay? So for doing that, actually I already identified the events. So for example, in 2005 the event was occurred in, the maximum flow was occurred in 2nd August. See here, 2nd August, the maximum flow was 4197 meter cube per second. So when you want to simulate it, you have to take at least 10-15 days before the event and 10-15 days after the event. Or else at least up to that particular event you have to take. Because today's flow is also dependent on yesterday's rainfall, day before yesterday's rainfall. So it has some lag effect. So you have to take at least 10-15 days before the event. Then if you are interested after the flood, how the flood is moving after the event, that also you can take. So for that purpose, we are taking 15 days before the event, 15 days after the event. Okay? So total we are taking 31 days. Okay? The first event was August 2. In the same way, another event was occurred in 12th August 2006, and another in 2007, 7th August it is occurred. I will tell you those dates. So now what we have to see, we have to run the model for that specific event. Okay? So first we will go with first event. So for that, same way, go to components. Just we need to create one more control specification file. That's it. Go to components and click on control specification file. Go to components, click on control specification file. Just create new. You can name it as event 1. Just for the clarity, you can name it as event 1. Okay? All of you reach here. Then click on create. Click on create. Just close that window. Same steps. Again go to components. check that event 1 is appear or not. If it is appear, just click on that. Here, when you click on this event 1 in the component editor, you have to specify those dates. Okay, so that particular event duration, I told you, right, it is happened on 2nd August, 15 days before, 15 days after. It means 18th July 2005 to 17th August 2005. Okay, enter the start date, 18th July 2005. Start time was 00. End time was 17th August. While naming, use the same format, 3 letters of the month and the year. And 17th August 2005. End time was 00. And time interval is 1 day. Just save it. Make sure the dates are same. 18th July 2005, 17th August 2005, and time interval is 1 day. Then go to compute. Sorry, need to create. So after that, just click on go to compute here. Go to compute. Create compute. Simulation run. Just name it as event 1. Just for the clarity, we are running for the event 1. Okay. Then click on next. See here, it will ask you what all you have to take. It has to take basin 1, meteorological 1 information, but here we are running for the event 1. So choose event 1. Then click on finish. Save it. Just all of you reach here. Any doubts? Just say, go to compute. Go to compute. Create compute. Simulation run. Just name it as event 1. Then you just run it for choose that event 1. When that control 1 is coming, you just choose. So now you can in the compute that event 1 is appear. So click on this event 1. Click on this event 1. Run it. All these are repetitive steps. Just run it. So if there is no error, anyone getting any error here? Just come to compute. Then click on event 1. Then here you just, this is the run symbol. Or else if you right click also, you will get compute. Both ways you can do. Then if there is no error, it will be fine, right? Yeah, to visualize the results, go to results. Go to results. Just you can minimize it. So now we are focusing on event 1. Just click on event 1. So what is happening in the sync? Just click on sync. Open the graph. So this is run just for that particular duration. Now you can see the blue one was simulated, the black one was observed. Our model was not able to capture that event. Okay? As we already given the observed data for the full period, so it took from that data. Okay? Again, one time you are giving me, no need to give us next time onwards. Okay? Then you can also see summary table. See, when you see in a full stretch, the performance was 0.68. But when you look into only the extremes, the performance was very low because it is not capturing. So, now what we need to do? We need to improve the performance, right? So for that we need to do calibration. Calibration is nothing but adjusting the parameters. What parameters we have given? Curve number, lag time. These two only we have given. Na? If Muskingum is there, the reach is there. In the Muskingum we have K and X. So those parameters also we need to optimize. Okay? I will show you how to do it manually, and then there is an option in the HMS. We can also do auto calibration. We can give some range, we can keep some iterations, then it will automatically run for that period. So we will get optimized parameters. Okay? So just when you are changing the parameters, you need to change in a you have to think and change. So for example, this model you take, this event you take, our simulated was low and observed was high. But so curve number, what you need to increase curve number, right? Because our curve number is directly proportional to runoff. So when you increase the curve number, then automatically runoff will increase. So when you are changing the parameter value, you have to keep this in mind and you need to change. Okay? Now we'll change the curve number. Come to compute, components. Where we have mentioned all those methods, the subbasin, right? So click on subbasin. The subbasin, in the last, it has specified 70, right? So make it 78. Make it 78. Hoping that it will increase. Okay. And next one is lag time. So lag time was what? If your flow was, for example, I'll show you that. Designs. See, here that observed peak was same, like it was attaining the same time. So lag time was correct. For example, your peak is here, simulated peak. The observed peak is this side. So we have kept lag time more. That time we need to decrease the lag time. So if you decrease the lag time, peak will attain very quickly. So based on that, you have to change the lag time. Okay? I think with here, except this part, remaining parts are matching with the observed flow, means pattern was matching. So lag time effect was less, but we'll try to decrease it. Same, go to components, the subbasin, the transform, make it 600 or 700. Now, it is like trial and error. Then save it. Save it. Then come to compute. Again same steps. Come to compute. We have changed the parameters, right? Now we will see with these changing parameters how the event 1 is coming. Just click on event 1. Just run the model. Come to results. Event 1. See the graph. It was little bit increased. compared to previous one, you see it was coming minus 0.33. Previous how much it is? 0.68. Minus 0.68, right? Now it reduced to minus 0.33. So means performance was increasing little bit. So in the same way, you have to change the parameters until it matches with the observed data. It is not one-time process. It is not like it will take time. It will take time adjusting the parameters. So it may take, because here it is only one subbasin. We are just changing like this. If you have multiple subbasins, it is very impossible to do it for each and every subbasin manually. Okay, there is option auto calibration. Okay, so to do it, I'll show you how to do it automatically. Auto calibration option is there. Optimization. Just save it one more time. So to auto calibrate it, go to compute. Go to compute. Here there is an option, optimization trial manager. Optimization trial manager. So click on new. You just make it event 1 and event 1, optimization 1, event event 1, optimization 1. Just click next. Same, it will ask you what basin model, what meteorological model you want to incorporate. I'll have to reach here. One more time. Yeah. Go to compute. Optimization trial manager. Click on new. Here you just name it event 1, optimization 1. Then click next. Then it will ask you to choose basin 1. Then it will ask you to choose meteorological 1. Then click OK. Yeah. Next, come to compute the component editor. Come to compute. Come to compute. So click on this event 1, optimization 1. Event 1, optimization 1. Here you need to specify at what period you are focusing on. Event 1 period. Compute. Go to compute. Okay, in the compute you will get this optimization trials. Come here. The compute one. So click on event 1, optimization 1. Here you have to give start date, end date, time interval. Before giving the start date, end date, it is always better to give time interval first. Otherwise, sometimes it is throwing error. It is better give 1 day first, then you give. What is the event 1 date? 18th July, right? 18th July 2005. End time was 17 August. 17 August 2005. Then 18th July 2005, 17th August 2005. Just save it. Just save it. After that, come to search in the component editor. Come to search. Method keyword is simplex. And here it is asking how many iterations you want to iterate. Usually when you are doing for real time, you have to keep maximum number of iterations. It is based on your computational capacity. For the demonstration purpose, we are going with 100. Okay. So if you keep more iterations, it will take more time to run. So we'll keep it 100. What this tolerance, what the tolerance indicates is, for example, your iteration 10, objective will fix the objective function next. But if you are at a 10th iteration, your objective function objective value NSE is coming 0.5. In the next 11th iteration, if it is coming 0.501, that means there was no significant improvement in the objective function. So it won't run for the 100 iteration, it will stop at 11th iteration itself. Okay, that is the tolerance. The objective, here we need to choose the objective function. Objective function was root mean square error. There are many objective functions you can choose. Peak weighted RMSE, it depends on what you are focusing on. Root mean square error means it will give you the error between observed and simulated. And our goal is to minimize that error. So goal is minimization. So start time was 18th July. 18th July 2005. Start time 00. Ending date is 17th August 2005. Enter time is 00. Save it. Okay? All of you reach here? One more time, this step one. Oh, okay. I'll just repeat it. So what we have mentioned here, dates, what method it is used to, simplex method, and maximum iteration, how many iterations, what is the tolerance. Our goal is to minimize the error between simulated and observed, and we are using RMSE as an objective function. Just save it. Yeah. Optimization is nothing but if you give set of parameters, set of range, for example, a CN. Next I will tell you. If you give some range for that parameter, it will check for each and every, for example, 0 to 100. If you do 100, it will take 100 times. It will take 100 CNs from those range. And it will check for each and every one, and whichever is given optimum value, then it will throw those parameters to us. Yeah. So we have specified the means at what time we are focusing on everything, right? But here under this optimization, which parameter we are focusing on? That parameter we need to add. Okay. For that, just right click on the event one optimization one. Right click on that. So here there is option called add parameter. Selected. Add parameter. Okay. Here just click on add parameter. And in the component editor, it will ask you which element you are focusing on. If you have so many subbases, then it will show you all the subbase numbers. You can do optimization all the subbasins at a time also, or sometimes what will happen, for one subbasin, one set of curve number range will fit. In another subbasin, that may not fit, because for example I will tell, in one subbasin it is covering more forest area, so curve number will be different. In another subbasin it is covering more urban, so there the curve number might be different, and in another subbasin where it was only barren land, their curve number will be different. So when you are optimizing it, it is always better to do it subbasin level. For each and every subbasin, you can do optimization separate by specifying separate range for each and every subbasin. But in our case, we are having only one subbasin. Both are same. All subbasins are subbasin one. Both are same. Let's choose subbasin one, and it is asking in subbasin one which parameter you want to optimize. We are focusing on curve number. Just select curve number. So initially we kept 70, right? That 70 came. Here you can play this minimum and maximum. For example, we'll try. See, when initially it was 70, when it was changed to 78, the performance little increased, right? So now we'll change it to curve number. That's it. I'm just giving minimum 65, maximum 85. Okay. So if it is locked no means what will happen? For example, sometimes if we say yes means it won't optimize. For example, if we have several subbasins, we'll add all those parameters. For some subbasins, already we are getting good value, so no need to optimize for that. So that time we can just, if you specify yes there, then it won't take this. If you specify no means it will optimize in between 65 to 85. Okay? Just click on save. Okay. What is our next parameter? Lag time, right? Again, go to here, event run optimization one, right click, add parameter, parameter 2, click on parameter 2, just click on event one optimization. Whenever you want to add parameters, you just right click here, that particular control, just click on add parameter, that will be added here. Just same, subbasin 1, which parameter? Lag time, just choose lag time. Initially we fit 600, so we just keep it 400 to 800 will play. Initial value, it should be in between these two, minimum and maximum. Okay, again otherwise it will throw error. Minimum and maximum value, change it to 400 to 800, then save it. All of you reach here. Then just click on event 1 optimization 1. Just click on event 1 optimization 1. Run this. If there is no error, it will run. Anyone getting error here? It is completed successfully. Restart. save. Suppose if something happen in between, you can just save it, close it, again you can open this project. From the same step you can start again. So no one getting any error, right? Now let's see what is the optimizer parameter. So to see that, go to results. Go to results. Click on event 1 optimization 1. Here optimize the parameters are there. It is showing the maximum value 85 and 800. It is taking the maximum value. When you click on sync 1 and you see the graph, there is a little bit change. And you see performance, it was before minus. So like this, you have to do optimization for the, like for example, here we have assigned only 2 parameters. If reach is there, the same way you have to specify minimum maximum values for the Muskingum K, Muskingum X also. Okay, once you are satisfied with this optimized parameters, for example, now this is minus 0.19, it won't happen in one stretch, it will take time. Okay, that too, we are making lumped model. It is not true, we are not considering spatial variability. So you won't get good performance here, because we are assigning only one curve number to entire basin, which is not possible. So won't expect good results here. But when you are doing real time, this is the procedure. So when you are satisfied with the optimization performance, then you take those optimizer parameters and update those parameters in the basin model and check for the validation period, how it is getting in the validation event. It is not coming back.
Sir, parameter 1 minimum value 60 and maximum value 85.
Yeah, it's okay. So it is clear what is calibration, what is validation. Yeah, same. So for example, now we got optimizer parameters, right? So if you take those parameters, you check it in the validation period. If its performance is good, then use the same parameter values for the period where you want. For example, you want to predict for the future, you just give the precipitation data for the future period, you run it.
We need to give the presentation.
Yeah. Yeah, you will get that. The first session, I think they told you how to get download data from GCM, right? I have CM IP6. They don't, I think they yeah. So you can get future precipitation data from GCM models. Yeah. If the performance was good in calibration, if it is not good in validation, again you come back to calibration, how to do it again. So it is an iterative process. Huh? I am showing you that it is giving the optimized parameters. After running the model, after here there is option. So these are the optimized values. 85 and 800. Okay, shall we do validation now? Time is there now. You are okay with time, right? It will take 20 minutes. Fine, right? Uh, so note down these optimized parameters and we'll update those parameters here. Components, come to basin, update those parameters. For the loss, we are getting 85. We are getting 85. For the lag time, we are getting 800. Save it. But if you want to run for the validation means that control we need to create. Means event 2 time was 28. It happened on 12th August 2006. So 15 days before that, 15 days after the event we are taking. Okay. So to create that control, go to components. Go to components. Click on Control Specification Manager. Click on Control Specification Manager. Click on New. Just name it Event 2. Event 2. Then click Create. Just close this window. All of you reach here. Same. The control specifications. Event 2, click on Event 2. Just specify the start time and the date. So it happened on 12th August. So start date was 28th July. 28th July 2006. And the end date was 27th August. 27th August 2006. End time was 00. Time interval is 1 day. Save it. 28th July 2006, 27th August 2006. Save it. So what next? Go to compute. Yeah, before that, you need to create this, right? For that, go to compute. Click on this compute. Click on this compute. Everybody following, right? Yes, sir. So, click on simulation run. If it run 2 or event 2, event 2, then click next. Model parameter has to take from basin 1, meteorological 1, and here it should take even 2 dates. Finish. Then click on, then go to compute. Just save it once. Go to compute. Click on event 2. Click on event 2. Run it. let's see those parameters are good in validation or not. So come to results. The event 2, under event 2, sync 1. See the graph. This is how it is predicting for the event 2 with those parameters. Okay, you can check NSE how it is. NSE was minus 0.848. It was not good. So whatever the parameters we have selected, whatever the parameters we have, the value which we have selected in the calibration period was not able to perform well in the validation period. So again we need to come back to event calibration. Again we need to optimize those parameters with different ranges. Then again take those parameters, keep it here, check the validation. If it is fine, if it is performing good, then it is done. So it is an iterative process. It is not one-time process. So assume that the performance was good. With those parameters, the model was performing good in both calibration and validation period. Then now we need to predict it for the future. Future nothing but here in our case it is 2007. Okay. So same again. Go to components, control specification file, create the events date for the event 3. Again run it. So go to components, create control specification file, click new, you can say edit, then click on create, just name it as event 3 or event 3 is also fine. So now here that is appear. Here you need to assign those dates. July 23rd. For the event 3, 23rd July 2007. Start time was 00 and end one was 22nd August 2007. Save it. All of you reach here. Same again. Go to compute, create compute, simulation run. The event 3. Next, lesson 1, 2 scale 1. Predict. It was done. We just click on save. Go to compute, that will appear. Event 3. Okay. Then just click on event 3, run the model, go to results, click on event 3, under sync 1, you can see the graph. It is coming like this. Summary table, it was 0.277. So time series table, so it will also give you this table, simulated flow at that particular event, the 2007. So what we can do in the across, we'll take this flow, and we will see with this flow how flood is going. Is it inundation is happening or not? So that we will check through the across. Okay. So till now clear? Any doubts? With this HMS is completed. Next we'll take this flow, this hydrograph. Then we'll use it for the across to see with this flow is it inundation is happening or not. Sir, actually, when you see, I'll tell you real example. See how to, when you are running real time, you have to take 30 years of data. So in 30 years of data, you may find almost 30 to 30 plus events. So when you are taking 30 plus events, you have to divide almost 60% of events for calibration, remaining percent for validation. So you have to do calibration for at least 20 events. So you will get optimized parameters perfectly. That is the real time when you are doing project. This is just for the 3 years. But when you are doing it for a long time period, you will get more events in the calibration. So model will accurately calculate those parameters. So then you have to use it for the validation. Okay, so that's why real time, all this real time itself, to run the model itself, it will take the 1 day. If we keep 20 events, if we have 20 subbasins, so in each subbasin, 20 events, you have to, like, all those parameters you have to arrange. So just to run the model for 100 iteration itself, it may take 2-3 hours. So we don't have that much time, we are just going with the simple 3 years later. Yeah. It is not limited with the data. If you have long-term basis data, at least if you do any kind of analysis with respect to this climate change or flood or drought, at least you require 30 years of data minimum. Okay, with this HMS is completed, and Saturday we'll start doing across, taking these values. Okay, you better copy these values. You can copy these values. Copy these values. Sir, you should understand, we are not predicting accurately here. In this less time period, you are unable to find out the accurate flow here. That's what I'm doing. It is all practice. That's what I'm telling. It will take this calibration itself. In my real case, it took 1 month. Just for the calibration, it took 1 month. It is not just 1 day process. That is what. Otherwise, all these models you can do set up in just in 3 hours. Yeah, you are true. Taking these values, whatever the flood inundation we are identifying, that is not at all true. We are, in this demonstration purpose, we are looking like what is the procedure. That is we are focusing on. True. It is very difficult to set up all those things in 3 hours. It is not possible. Yeah. You can just directly copy this. All of you copy this, because this is our observed flow, this is our inflow, means that particular outlet inflow. So this inflow we will use it for the across model to see how the flood inundation is happening. You just select all this, just right click, or else you just press Ctrl C, open Excel. Open Excel, you just paste it. Okay.
Do you have any exact and accurate data with which we got very good annotation? Annotation maps.
That I can't give.
Just for
I'll show you.
represent purpose only. Just show us how much area got inundated. Can we calculate the extra area?
Everything we are showing, but it is not accurate. That's it. This model.
What I'm asking. But we have first type of data. Just show us how much.
No one will use it.
No, don't give it. Just show us. Give us.
Sure, sure.